The oldest mysteries on Earth are not hidden because no one has looked for them. They're hidden because people have been looking at them for centuries without realizing what they were seeing. A lonely hill becomes a buried pyramid. A cave wall turns out to be the entrance to an underground city. A ruined temple reveals another, even older monument beneath its foundations. Again and again, the ancient world has shown that appearances can be remarkably deceptive. What seems ordinary can conceal extraordinary history. What appears fully explored can still hold unanswered questions. That is why every discovery has the power to change far more than a single archaeological site. It can change the story we tell about an entire civilization, and sometimes about humanity itself. On Spain's southeastern Mediterranean coast, near the mouth of the Segura River, lies La Fonteta, an ancient Phoenician settlement buried beneath sand and silence. Nearly 3,000 years ago, it was one of the most important gateways between the Mediterranean world and the Iberian Peninsula. Today, the city remains, but its harbour, the very reason for its existence, has seemingly vanished from history. Archaeological excavations conducted during the late 20th century revealed the remains of a fortified Phoenician settlement dating between the 8th and 6th centuries BCE. Beneath layers of dunes, researchers uncovered massive defensive walls, industrial zones, imported luxury goods, and evidence of extensive maritime trade. Yet the most important structure expected at such a site, a major harbour, remains elusive. At first glance, La Fonteta appears far less impressive than famous sites such as Machu Picchu, Petra, or Baalbek. There are no colossal temples, giant statues, or megalithic blocks weighing hundreds of tons. Yet beneath its modest appearance lies a different kind of mystery, evidence of sophisticated engineering knowledge that seems unexpectedly advanced for its age. The settlement occupied a highly challenging environment near a river delta. Modern civil engineers recognize such landscapes as difficult locations for permanent construction. River mouths experience constant sediment deposition, flooding, shoreline migration, groundwater fluctuations, and soil instability. Even with modern surveying equipment, constructing durable infrastructure in such environments requires careful planning. Yet Phoenician builders established a thriving urban centre here nearly 3,000 years ago. The city's defensive walls reached thicknesses estimated between 4 and 5 meters. Excavations revealed reinforcement systems and regularly spaced structural supports that appear designed to distribute stress and prevent large-scale collapse. Some researchers have suggested these features may have improved resistance against seismic activity or foundation movement. The intriguing question is not whether the walls worked. They clearly did. The mystery is how engineers of the 8th century BCE acquired enough practical understanding of structural behaviour to implement solutions that resemble concepts used in modern engineering. No surviving technical manuals explain their methods, and no architectural blueprints have been discovered. The knowledge itself seems to have vanished while the walls remained. The greatest puzzle surrounding La Fonteta concerns something that should have been impossible to lose: an ancient harbour. Historical and archaeological evidence strongly suggests that La Fonteta functioned as a major maritime trading centre. Imported materials found at the site include Greek pottery, Egyptian-style scarabs, ivory objects, luxury ceramics, and goods originating from regions hundreds or even thousands of kilometres away. Such trade networks do not emerge without maritime infrastructure. Ships needed protected docking areas, cargo required loading facilities, merchants needed warehouses, and navigation demanded channels deep enough for vessels. A functioning harbour should have existed, yet archaeologists cannot fully locate it. This is one of the most fascinating enigmas in Mediterranean archaeology. 3,000 years ago, the shoreline stood dramatically closer to the settlement than it does today. Geological studies indicate that sediment carried by the Segura River gradually transformed the landscape. Coastal processes deposited enormous quantities of sand and silt over centuries. What was once open water became marshland, dunes, and agricultural terrain. In effect, nature rewrote the map. Modern satellite imagery reveals little resemblance to the ancient coastline. The harbour that sustained La Fonteta may now lie buried beneath meters of sediment, hidden beneath modern terrain, or destroyed by centuries of environmental change. The scale of this transformation is difficult to visualize. Consider the ancient harbour of Ephesus in modern Turkey. Once located directly on the coast, it now lies several kilometers inland because of river sediment accumulation. Similar processes altered the landscape around Miletus, Ostia, and numerous other ancient ports throughout the Mediterranean. La Fonteta may represent an even more extreme case. Archaeologists know the city depended on maritime trade. They know ships arrived here, and they know goods flowed through the settlement. Yet the infrastructure enabling that activity remains largely invisible. It is a port city without a visible port, a maritime centre whose harbour has disappeared. Few archaeological mysteries illustrate the power of geological change so dramatically. The harbour mystery raises another question. How did Phoenician engineers understand coastal dynamics well enough to establish a successful port in the first place? Modern harbour construction requires analysis of sediment transport, currents, wave energy, seasonal flooding, and shoreline stability. Engineers use mathematical models, satellite observations, and decades of environmental data. Phoenician builders possessed none of these tools. Yet their trading network stretched across more than 3,000 kilometers of coastline, connecting the Levant with North Africa, Sardinia, Sicily, southern Spain, and beyond. The success of this network suggests practical expertise accumulated over generations. La Fonteta may represent evidence of an engineering tradition based not on written science but on centuries of observation and experience. The problem is that archaeology can observe the results of that knowledge but struggles to reconstruct the intellectual processes behind it. The harbour may be gone, but the sophistication required to create it remains visible in the city's existence. Excavations have revealed evidence of metallurgical activity within the settlement. This discovery transformed scholarly understanding of La Fonteta. For many years, researchers viewed Phoenician colonies primarily as commercial outposts. Increasing evidence now suggests that some functioned as manufacturing centres as well. Metalworking debris, furnaces, and industrial remains indicate local production activities. The implications are significant. Iron technology was spreading across the Mediterranean during this period. Mastery of smelting and metal processing required precise temperature control, fuel management, ore selection, and specialized knowledge accumulated through experimentation. Experimental archaeology demonstrates that producing high-quality iron consistently is remarkably difficult, even when modern researchers attempt to replicate ancient methods. Tiny variations in furnace temperature can drastically affect results, impurities can ruin an entire production cycle, and airflow must be carefully controlled. Yet ancient metallurgists achieved results sufficient to support expanding regional economies. At La Fonteta, the full technological system remains only partially understood. Researchers have identified evidence of production, but they have not fully reconstructed the process. The technology exists in fragments, and the knowledge that created it remains incomplete. The artifacts discovered at La Fonteta tell a remarkable story. Objects originating from distant cultures arrived at this relatively small settlement on the edge of the Iberian Peninsula. Such findings reveal an interconnected world centuries before the rise of Rome. Comparisons with modern trade networks are tempting. Although ancient commerce operated on a vastly smaller scale, the underlying principle was similar. Specialized regions exchanged resources, technology, luxury goods, and information across enormous distances. The challenge lies in understanding navigation. Phoenician sailors crossed open waters without compasses, GPS, radar, or accurate longitude calculations. Ancient sources suggest they navigated using stars, prevailing winds, coastal landmarks, and accumulated experience. Yet historians continue debating how precise these methods truly were. The repeated success of long-distance voyages suggests a level of maritime expertise that remains difficult to quantify. Once again, the achievements are visible, while the underlying techniques remain partially hidden. What do you think happened to La Fonteta's lost harbour? Was it buried by nature, destroyed by disaster, or is it still waiting to be discovered beneath the sands? Share your thoughts in the comments below. On a rocky promontory overlooking the Tyrrhenian Sea in western Italy lies Populonia ***, the only major Etruscan city built directly on the coast. Today it appears as a quiet archaeological site, but more than 2,000 years ago it may have been one of the largest iron processing centres in the ancient world, a place where millions of tons of ore were transformed into metal using technologies that archaeologists still struggle to fully reconstruct. Unlike many lost cities hidden beneath jungle or desert, Populonia was never completely forgotten, yet its greatest secret remained unnoticed for centuries. Massive hills surrounding the site were long assumed to be natural formations, until modern archaeological investigations reveal that many of them were actually gigantic accumulations of iron smelting waste. Beneath these seemingly ordinary mounds lay evidence of an industrial landscape unlike anything previously associated with the Etruscans. Most ancient cities are remembered for temples, palaces, or defensive walls, but Populonia is different because its true monument is waste. Archaeologists estimate that the region once contained millions of tons of metallurgical slag, the byproduct of iron production, with some deposits reaching several meters in depth and covering extensive portions of the coastline. The sheer scale suggests industrial activity operating continuously across centuries, creating an immediate paradox. The Etruscans are often portrayed as a sophisticated but relatively small civilization that flourished before Roman domination. Yet the volume of material processed at Populonia appears closer to what one might expect from a major industrial centre than from a modest ancient city. The source of this wealth lay across the water on the island of Elba, whose iron deposits rank among the richest in Europe, and ancient ships transported ore from the island to Populonia, where it was smelted, refined, and distributed throughout the Mediterranean. The basic process is understood, but the scale is not. Among all the mysteries surrounding Populonia, none may be more fascinating than the performance of its iron industry. Extracting iron from ore is not a simple task, as the process requires temperatures often exceeding 1,100 degrees Celsius, making it difficult not only to achieve such heat, but even harder to maintain it consistently. Modern metallurgical operations rely upon precise temperature monitoring, controlled airflow, and extensive understanding of chemical reactions. Yet the Etruscans possessed none of these advantages. They had no thermometers, no modern furnaces, no steel refractory materials, and no chemical laboratories. Despite this, analyses of ancient slag indicate surprisingly efficient extraction rates, with remaining waste often containing less recoverable iron than researchers would expect from primitive smelting systems, suggesting that Populonia's metallurgists were remarkably successful at extracting metal from ore. How they achieved this remains controversial. experimental archaeologists have attempted to recreate Etruscan furnaces using traditional materials, and while some experiments successfully produced iron, they often required extensive experience and repeated adjustments, making it difficult to reproduce ancient efficiency even under controlled modern conditions. The challenge becomes even more striking when compared with other ancient societies, many of which lost significant quantities of metal within slag deposits due to difficulties in controlling furnace chemistry. At Populonia, however, evidence suggests operators frequently approached levels of performance that appear unexpectedly advanced for the period. Some researchers propose that generations of practical experimentation allowed Etruscan craftsmen to develop highly refined empirical knowledge, while others argue that furnace designs themselves may have incorporated innovation still poorly understood because so few complete examples survive. The result is a rare archaeological mystery. We possess the waste, we know the outcome, yet the precise methods remain largely invisible. One of the greatest frustrations for archaeologists is that the enormous slag fields survived far better than the facilities that produced them, as millions of tons of waste remain while most furnaces do not. The structures responsible for this industrial output were built largely from materials vulnerable to erosion, recycling, and destruction over centuries, forcing researchers to reconstruct entire technological systems from fragments. It is like discovering the tailings of a modern mining operation thousands of years in the future while finding only a few pieces of machinery, which is essentially the situation at Populonia. Because the physical evidence is incomplete, several competing theories exist. Some scholars suggest that furnace placement exploited coastal winds to intensify combustion naturally, while others propose sophisticated bellows systems capable of generating airflow far greater than traditionally assumed. Neither explanation fully resolves the problem, and the more researchers calculate the energy requirements of large-scale iron production, the more impressive the engineering becomes. The slag mountains themselves raise additional questions, as industrial waste is often imagined as chaotic accumulation, yet Populonia does not always fit that model. Archaeological surveys indicate patterns suggesting deliberate organization, management, and long-term planning, with waste concentrated in designated areas rather than randomly scattered across the landscape. This implies administration, meaning someone had to coordinate deliveries of ore, manage fuel supplies, organize labor, and maintain production schedules. Although the existence of such logistical systems is rarely visible in the archaeological record, the scale of activity suggests they must have existed, and in effect, Populonia may have functioned less like a traditional city and more like a highly integrated industrial complex. Iron production consumes enormous amounts of fuel, introducing another mystery. Every furnace required charcoal, charcoal required wood, and wood required forests, and modern calculations suggest that sustained metallurgical activity on the scale observed at Populonia would have consumed vast quantities of timber over centuries. This raises critical questions. Where did all that fuel originate? How were forest resources managed, and why did complete ecological collapse apparently not occur immediately? Comparable questions arise at other ancient industrial centres, such as Roman mining districts in Spain that transformed landscapes through large-scale extraction, or ancient copper production in Cyprus that required extensive fuel consumption. Yet Populonia appears to have maintained iron production for generations, while remaining economically viable. Some researchers suspect that extensive woodland management programs existed, while others believe fuel was imported from broader regions than traditionally assumed, though direct evidence remains limited. Another overlooked mystery involves transportation. As ore travelled from Elba to Populonia, fuel travelled from inland forests, and finished metal travelled across Mediterranean trade networks, with each stage requiring coordination. Ancient ships lacked engines. Ports lacked cranes powered by machinery, and navigation depended on environmental conditions, yet the system worked not occasionally but repeatedly for centuries. The comparison with later civilizations is revealing, as the Roman Empire developed vast transportation networks supported by roads, ports, and administrative infrastructure, while Populonia achieved large-scale industrial activity before Rome reached its greatest power. This raises an important possibility that the organizational capabilities of the Etruscans may have been significantly more sophisticated than traditionally acknowledged. If the Etruscans could achieve such remarkable iron production efficiency with the tools available to them more than 2 millennia ago, what crucial piece of knowledge do you think has been lost to history? Share your thoughts in the comments below. On the edge of Peru's coastal desert, nearly 200 kilometers south of Lima, stands a structure that should not look the way it does. More than 5 centuries after the fall of the Inca Empire, the walls of Tambo Colorado still display traces of red, yellow, and white pigments. In one of the driest regions on Earth, the colors remain. The question is simple: how? Spanish chroniclers recorded the site shortly after the conquest of the Inca Empire in the 16th century. Systematic archaeological investigations began centuries later, revealing one of the best preserved administrative centers ever discovered along the coastal branch of the Inca road system. Most ancient painted structures share the same fate. Time erases them. The brilliant blues of ancient Egypt faded. The painted temples of Greece lost nearly all visible color, and Roman buildings that once displayed vibrant pigments survive mostly as bare stone and plaster. Yet Tambo Colorado presents a different story. Visitors today can still identify extensive sections of red, yellow, cream, and white decoration across walls, corridors, and ceremonial spaces. Archaeological analysis indicates that the pigments were primarily mineral-based. Red pigments likely came from iron-rich hematite, yellow tones appear linked to iron oxides and clay minerals, and white pigments were probably derived from calcium-rich compounds. The mystery is not where the colors came from, the mystery is why they remain. Laboratory studies show that mineral pigments alone cannot fully explain such preservation. Pigments require binders, and without a binding agent, wind erosion, temperature fluctuations, and occasional rainfall events would gradually remove them. Researchers have proposed several possibilities. Organic binders derived from plant extracts, cactus compounds, animal proteins, or natural gums may have been used. The problem is that many organic substances decompose over centuries, leaving little trace for modern scientists to analyze. This creates a remarkable archaeological puzzle. We can see the results of the formula, but not necessarily the formula itself. The environmental challenge makes the mystery even greater. Although the Peruvian coast is extremely dry, it is not completely stable. El Niño events periodically bring heavy rainfall capable of damaging adobe architecture. Seasonal temperature variations produce expansion and contraction within wall surfaces, while wind-driven sand continuously abrades exposed structures, yet significant portions of the original coloration remain visible. Comparisons with other adobe civilizations are revealing. Many painted adobe structures associated with the Moche, Chimu, and Nazca cultures have suffered far greater pigment loss. Even where preservation is exceptional, the degree of visible color retention at Tambo Colorado remains unusual. Some specialists argue that the answer may lie in a sophisticated combination of pigment chemistry, wall preparation, environmental conditions, and maintenance practices performed during the Inca period. However, no single explanation has yet solved the mystery completely. the colors of Tambo Colorado continue to challenge assumptions about ancient material science. At first glance, Tambo Colorado appears less technologically impressive than Machu Picchu or Sacsayhuaman. There are no gigantic polygonal stones weighing dozens of tons and no dramatic mountain terraces stretching across entire valleys. Yet the site's engineering achievements become increasingly impressive when examined closely. Unlike many famous Inca monuments, Tambo Colorado was built primarily from adobe. Adobe construction sounds simple, but in reality it presents significant engineering challenges. Adobe bricks shrink during drying, crack when moisture levels fluctuate, and can develop structural weaknesses if mixtures are inconsistent. Large walls are particularly vulnerable to deformation over time. Despite these limitations, many walls at Tambo Colorado remain remarkably straight. Angles are carefully controlled, corridors maintain consistent dimensions, and architectural symmetry appears repeatedly throughout the complex. Modern engineers understand that achieving such consistency requires careful control of material composition. The ratio between clay, sand, moisture, and organic reinforcement must be managed with precision. The question becomes obvious. How did Inca builders standardize construction materials across a large complex without modern testing equipment? No written construction manuals survive, and no engineering drawings survive. Yet the finished architecture demonstrates repeatable quality control. The knowledge clearly existed, but the documentation does not. Another mystery emerges from the site's geometry. Tambo Colorado was not assembled randomly. The complex follows a highly organized layout consisting of plazas, ceremonial spaces, administrative rooms, storage facilities, and interconnected corridors. Such planning requires measurement. Today, architects rely on rulers, laser surveying equipment, GPS systems, and computer modeling. The Inca possessed none of these tools. Even more intriguing, they left behind no conventional writing system capable of preserving architectural plans in the way Egyptian, Roman, or Mesopotamian civilizations sometimes did. Yet the geometry is undeniable. Researchers believe the Inca employed standardized measurement systems, possibly based on body proportions, calibrated chords, or modular units used throughout the empire. Some studies suggest recurring dimensional relationships across multiple Inca sites separated by hundreds of kilometers. However, definitive evidence remains elusive. The architecture demonstrates measurement, but the measurement system itself remains largely invisible. It is similar to discovering a modern skyscraper while losing every blueprint used to build it. Peru sits along the boundary where the Nazca Plate descends beneath the South American Plate. This geological collision generates some of the most powerful earthquakes on Earth. Over the past 5 centuries, the region has experienced numerous destructive seismic events. Entire cities have been damaged or rebuilt, colonial structures have collapsed, and modern buildings continue to require advanced seismic engineering. Yet Tambo Colorado remains standing. The survival of the site raises important questions about Inca structural knowledge. Archaeologists have identified several potentially significant characteristics. Thick walls distribute forces more effectively, relatively low building heights reduce instability, and internal layouts divide structural loads among multiple sections, rather than concentrating them in single massive chambers. These features resemble principles recognized in modern earthquake-resistant architecture. Of course, Inca builders did not possess seismographs or plate tectonic theory. However, practical observation accumulated over generations may have produced engineering solutions adapted to a seismic landscape. This pattern appears repeatedly throughout the Inca world. At Machu Picchu, Ollantaytambo, and Cusco, structures demonstrate extraordinary resistance to earthquakes. Tambo Colorado may represent a coastal adobe version of the same engineering philosophy. The Peruvian desert presents another challenge. Daytime temperatures can become intense, solar radiation is powerful, and water is scarce. Maintaining comfortable interior environments under such conditions is difficult even with modern technology. Yet many rooms at Tambo Colorado appear designed to regulate temperature naturally. Thick adobe walls possess high thermal mass. During the day they absorb heat slowly, and at night they release stored energy gradually. This process reduces temperature extremes inside buildings. Researchers also note that doorway placement, corridor alignment, and courtyard organization may have encouraged natural airflow throughout the complex. The result resembles passive climate control systems used by modern sustainable architects. What is striking is that these solutions emerged centuries before the development of thermodynamics as a scientific discipline. The builders understood the environment well enough to shape architecture around it. Overlooking the Atlantic coast of northwestern Spain at the mouth of the Minho River in Galicia lies the Castro of Santa Trega. More than 2,000 years ago, an entire stone city was built on a windswept mountain summit. Today, archaeologists can see the walls, they can map the streets, but they still cannot fully explain how its builders achieved such remarkable engineering precision without written plans, advanced instruments, or sophisticated machinery. Although local people had long known of the ruins, systematic archaeological excavations began in the early 20th century, and what researchers uncovered was astonishing. Hundreds of stone structures spread across nearly 20 hectares, making Santa Trega one of the largest known Iron Age settlements in the Iberian Peninsula. The discovery transformed understanding of the ancient Castro culture, as what had once been viewed as scattered tribal communities suddenly appeared capable of creating large, highly organized urban settlements. The first mystery begins with location, as most ancient civilizations preferred valleys, river plains, or fertile lowlands, because these environments reduced construction costs and simplified agriculture. Yet Santa Trega ignored those advantages entirely. The settlement occupies a mountain rising approximately 340 meters above sea level, where strong Atlantic winds strike the summit throughout the year, and rainfall in Galicia frequently exceeds 1,000 millimeters annually, sometimes reaching nearly 2,000 millimeters in certain regions. Modern engineers understand the difficulties of building on steep terrain, where every structure requires stable foundations, water runoff must be controlled, landslides must be prevented, and access routes must remain functional. Yet the ancient builders transformed the mountain into a functioning urban landscape. Researchers estimate that extensive leveling and terrace construction would have been necessary before many of the houses could even be built, and massive quantities of stone had to be moved across slopes without wheel transport systems, comparable to later Roman infrastructure, leaving the question unresolved. How was such a large-scale landscape engineering project organized and executed by an Iron Age society? Among all the mysteries of Santa Trega, perhaps none is more intriguing than the remarkable precision of its circular architecture, as hundreds of houses discovered throughout the settlement are round or oval in shape, appearing simple at first glance, but revealing something unexpected upon closer examination. Many walls follow smooth geometric curves with impressive consistency, and their circular plans are not random approximations, but instead display a level of regularity suggesting intentional measurement. Modern surveyors can create perfect circles using lasers, steel tapes, and digital instruments. Yet the builders of Santa Trega possessed none of these technologies, and even with a simple rope and stake method, maintaining consistent geometry across hundreds of structures would require a standardized construction process and skilled builders. Though no written manuals survive and no measuring tools have been found to explain the system. Archaeologists often compare these houses with circular structures found throughout Celtic Europe, but Santa Trega presents a particularly concentrated example, where entire neighbourhoods display repeated geometric patterns that appear to follow shared design principles. The mystery deepens when considering construction accuracy, as stone walls composed of irregular granite blocks somehow maintain smooth, external curves over significant distances, requiring continuous adjustment during construction, where every stone placement affects the final geometry. Modern masonry studies show that curved walls demand more planning than straight walls, because each block must accommodate changing angles, increasing labour requirements and complexity, suggesting that the builders were not simply stacking stones, but were shaping space according to geometric rules that remain largely invisible to archaeology. The circular houses may have served practical purposes extending far beyond aesthetics, as aerodynamic studies demonstrate that circular structures experience reduced wind pressure compared with rectangular buildings, with strong gusts being diverted around curved surfaces rather than striking flat walls directly. This is particularly relevant at Santa Trega, where the settlement faces the Atlantic Ocean and experiences powerful coastal winds, and modern architects designing structures for hurricane-prone regions sometimes employ similar principles. Did Iron Age builders understand aerodynamic efficiency? Probably not in mathematical terms, but centuries of observation may have allowed them to recognize which building forms survived storms most effectively, leading to a fascinating possibility. Empirical engineering developed through generations of experimentation rather than formal science. Water may represent Santa Trega's greatest technical challenge, as a settlement containing hundreds or perhaps thousands of inhabitants required reliable water supplies, despite being located on a mountain summit, and equally important was drainage. Heavy rainfall can destroy settlements through erosion, as water flowing downhill gains energy, carving channels and undermining foundations. Yet despite this threat, large portions of Santa Trega remained stable for more than 2 millennia. Researchers have identified pathways, terraces, and open spaces that may have functioned as components of an integrated drainage network. And rather than relying on monumental canals like those of ancient Rome, the settlement appears to have used subtle topographic control. In modern engineering terms, this resembles passive water management, where gravity performs the work and the landscape itself becomes infrastructure, though the challenge remains that much of the original system has vanished, leaving archaeologists to see fragments while struggling to reconstruct the complete hydraulic design. Another mystery emerges when viewing Santa Trega from above, as the settlement does not appear chaotic but instead shows buildings clustering into organized groups, pathways connecting neighborhoods, open areas occurring in strategic locations, and circulation routes that seem intentional. This raises a difficult question. How did planners coordinate construction across such a large settlement without written architectural drawings? Today, urban planning relies on maps, measurements, and standardized documentation, yet no evidence suggests that Santa Trega possessed comparable systems, and still the city functions as an integrated whole. Comparisons with other Iron Age sites reveal that Santa Trega was not merely a collection of isolated houses, but behaved more like a planned urban environment, though the intellectual process behind that planning remains invisible. One of the strongest indicators of advanced technical knowledge is standardization, and at Santa Trega, researchers repeatedly encounter recurring architectural patterns where house dimensions often fall within similar ranges. Construction methods show notable consistency, and building layouts share common characteristics. Such uniformity rarely emerges spontaneously, as in most societies, standardization reflects the transmission of specialized knowledge, where skilled builders teach apprentices, techniques become refined, and construction traditions persist for generations. But here lies the mystery. The knowledge survived long enough to build an entire city, then it disappeared, leaving no surviving texts to explain the methods, no engineering manuals, and no architectural diagrams to reveal how measurements were made, with only the finished products enduring. Perched on a windswept plateau more than 1,100 meters above sea level in central Spain, stands one of the most extraordinary walls ever built. Stretching approximately 2.5 kilometers around the historic city of Avila, rising up to 12 meters high and reinforced by nearly 90 massive towers, the walls of Avila appear so complete and so perfectly preserved that many visitors assume they must have been reconstructed, yet much of what stands today is original. Nearly 1,000 years after construction, the walls remain one of the greatest surviving engineering achievements of medieval Europe, and one of its least understood. Unlike lost cities hidden beneath jungles or deserts, the walls of Avila were never truly lost, as they have dominated the landscape since the late 11th century. Historical records suggest major construction began shortly after the Christian reconquest of the region around 1090 AD. Yet, despite centuries of study, historians still possess remarkably little information about the actual engineering process. No original construction plans survive, no technical manuals survive, and no detailed records explain how thousands of workers transformed enormous quantities of granite into one of the most impressive defensive systems ever built in Europe. The wall survives, but the knowledge behind it largely does not. The greatest mystery begins with something many visitors never notice. The wall is not simply large, it is geometrically precise. Modern surveys reveal an extraordinary consistency throughout the structure, where tower spacing follows recognizable patterns, wall thickness remains surprisingly uniform across long distances, gates align with major routes and natural terrain features, and defensive visibility between towers appears carefully calculated. This may not sound remarkable until one considers the technological limitations of the 11th century, when engineers today rely on GPS, laser scanners, total stations, satellite imagery, and computer modeling to design large fortifications, tools that medieval builders did not possess. Yet somehow they created a defensive perimeter enclosing roughly 33 hectares while maintaining a level of geometric control that remains impressive even by modern standards, raising a simple question: how? Researchers have proposed the use of ropes, measuring rods, sighting techniques, and astronomical observations, explanations that undoubtedly account for part of the process. But many specialists argue that the overall precision suggests a highly organized surveying system, far more sophisticated than commonly imagined. The mystery becomes even more intriguing when compared with other ancient and medieval engineering achievements, such as the builders of the Great Pyramid maintaining orientation errors measured in fractions of a degree, the planners of Roman military camps producing standardized layouts across vast territories, and the engineers of Machu Picchu aligning architecture with mountainous terrain while maintaining remarkable geometric consistency. The walls of Avila belong to this same category of achievement, where the final result is visible but the intellectual process behind it remains largely hidden. The walls are often described as a military structure, but that description may be incomplete, because when examined from above, the fortification behaves less like a barrier and more like an integrated system in which every tower influences adjacent towers, every gate affects movement patterns, and every wall segment contributes to defensive visibility. The placement of structures appears coordinated rather than improvised, even though military historians frequently note that medieval fortifications often evolved gradually over centuries, with sections added, modified, rebuilt, or expanded according to changing needs. Avila feels different, as its overall coherence creates the impression of a master plan. And if that impression is correct, someone had to envision the entire system before construction began. This raises a fascinating question about who possessed the mathematical and engineering knowledge necessary to design such a project, yet no name survives, no architect is known, and no engineer is identified, leaving one of Europe's greatest construction achievements effectively anonymous. Another mystery emerges when examining the raw materials, as the walls were built primarily from granite, a material that is durable but notoriously difficult to work with. Many stones incorporated into the structure weigh hundreds of kilograms, with some weighing considerably more, and each block required extraction from quarries, transport across rugged terrain, lifting into position, and precise placement. Modern construction companies accomplish similar tasks using hydraulic cranes, steel cables, diesel engines, and advanced lifting equipment, technologies that the builders of Avila did not have. Researchers estimate that medieval construction projects of this scale required moving tens of thousands of tons of stone, making the logistics alone staggering. Comparisons with other famous stone monuments highlight the challenge, such as Roman engineers at Baalbek, transporting blocks weighing hundreds of tons, Inca builders at Sacsayhuaman moving massive stones across mountainous landscapes, and the builders of the Great Pyramid positioning millions of limestone blocks with astonishing accuracy. In each case, modern scholars can propose plausible methods, yet complete certainty remains elusive, and Avila presents the same puzzle on a medieval scale, where the walls demonstrate that the builders succeeded but the exact methods remain debated. Perhaps the most overlooked question is not how the walls were built, but why they're still standing, as they have survived nearly a millennium of environmental stress, including temperature fluctuations, rain, wind, freeze-thaw cycles, ground movement, human activity, wars, and neglect. Despite all of this, enormous portions remain intact, and from an engineering perspective, this longevity is extraordinary. Modern structural analysis suggests that the walls distribute loads extremely effectively, with their thickness, tower arrangement, foundation design, and material selection creating a remarkably stable system. Yet medieval builders lacked modern structural equations, computer simulations, finite element analysis, and geotechnical software, and still they produced a structure capable of surviving for centuries. Some researchers argue that empirical knowledge accumulated through generations may explain the achievement, as builders learned from previous projects and refined techniques through experience, an explanation that is probably true but also highlights another mystery: how much engineering knowledge has been lost. The walls themselves may preserve evidence of expertise that no longer exists in written form. One theory suggests continuity with Roman engineering traditions. The Romans mastered advanced construction techniques, and although much of this knowledge was thought lost after the empire's decline, Avila's design shows similarities in its geometry, layout, and integration with the landscape. Some historians believe this knowledge may have survived through local craftsmen and institutions. If so, the walls of Avila could reflect a lingering legacy of Roman engineering, though evidence remains inconclusive. The monumental gates of Avila introduce another engineering paradox, as large openings are traditionally weak points in defensive walls, with every gate creating structural vulnerabilities and every opening reducing overall strength. Yet the principal entrances of Avila remain among the most impressive elements of the entire complex, with massive towers flanking the gateways and large stone arches supporting tremendous loads, allowing the structures to endure for centuries without catastrophic failure. Modern engineers understand the mechanics involved. as arches transfer forces efficiently into supporting masonry, and compression-based construction can be extraordinarily durable. But the mystery is not whether the design works, rather how accurately medieval builders understood these principles without modern theoretical frameworks. Their practical results suggest knowledge that exceeded what many people assume medieval engineers possessed. In Volterra, Tuscany, Italy, ancient stones preserve a technological mystery that refuses to disappear. Long before Rome dominated the Mediterranean, the Etruscans transformed this rugged summit into a carefully planned sacred and political centre. Today, archaeologists call it the Volterra Acropolis. At first glance, the ruins appear modest compared with the pyramids of Egypt or the terraces of Machu Picchu. Yet beneath the surviving foundations lies a deeper puzzle. The mystery is not what the Etruscans built, but how they achieved such sophisticated engineering while leaving behind almost none of the technical knowledge that made it possible. The Acropolis occupies the highest point of Volterra, a city that rises more than 500 meters above sea level. Archaeological excavations conducted during the 20th century reveal temples, roads, foundations, drainage systems, and evidence of urban planning dating primarily to the Hellenistic Etruscan period between the 4th and 2nd centuries BCE. What researchers uncovered was not merely a collection of buildings, but an integrated engineering system constructed on one of the most challenging landscapes imaginable. The location itself immediately presents a problem, as Volterra stands atop a geological formation known for instability. Even today, portions of the surrounding terrain experience erosion, landslides, and gradual slope movement, prompting modern engineers to continuously monitor the region because the underlying soils and sedimentary layers can become unstable under changing environmental conditions. Yet, more than 2,000 years ago, Etruscan builders selected this difficult terrain and successfully erected monumental structures capable of surviving centuries of weather, earthquakes, and human occupation. The first mystery emerges from the site's geometry, as when archaeologists mapped the Acropolis, they discovered evidence of deliberate planning rather than organic growth. Building orientations, street alignments, and temple placements reveal consistent geometric relationships, which may sound ordinary until one considers the terrain. Creating regular alignments on a flat plane is relatively straightforward, but doing so on an uneven hilltop requires surveying techniques capable of compensating for changing elevations, irregular rock formations, and shifting slopes. Modern surveyors use total stations, laser scanners, GPS systems, and digital terrain models. Yet Etruscan engineers possessed none of these technologies. Nevertheless, the layout demonstrates a level of spatial organization suggesting careful measurement and advanced planning. Comparisons with contemporary settlements reveal how unusual this achievement may have been, as many Iron Age communities expanded incrementally, producing irregular street networks that reflected local geography, whereas Volterra displays evidence of intentional organization resembling urban planning traditions later perfected by Roman engineers. How Etruscan surveyors achieved this accuracy remains largely unknown. The puzzle deepens when researchers examine the foundations, as unlike modern construction projects, Etruscan builders could not conduct geotechnical drilling programs or computer-based stability analyses, nor did they possess mathematical models describing soil mechanics. Yet the placement of major structures suggests a remarkable understanding of the hill's geological behavior. Several surviving foundations appear positioned on the most stable portions of the summit, leading some archaeologists to argue that centuries of accumulated empirical knowledge allowed Etruscan builders to identify load-bearing zones through observation alone. while others believe their practical understanding of geology may have been far more sophisticated than surviving evidence suggests. The challenge becomes clear when compared with modern construction standards, as contemporary engineers often spend months evaluating ground conditions before placing large public buildings, whereas the Etruscans somehow achieved long-term structural stability without access to any of the instruments modern engineers consider essential. Water management introduces another layer of mystery, as ancient builders understood that water is often more dangerous than gravity. Rainwater infiltrating soil can trigger erosion, weaken foundations, and destabilize slopes, making control of runoff critical on elevated sites such as Volterra. Excavations have revealed traces of drainage systems integrated directly into the Acropolis, including channels, carefully graded surfaces, and engineered pathways designed to guide water away from important structures. The remarkable aspect is that much of this hydraulic system was effectively invisible, as instead of relying solely on large open canals, the builders appear to have manipulated slopes, surface gradients, and subsurface features to manage water movement. Modern civil engineers frequently describe drainage as one of the most difficult aspects of hillside construction, because failures often remain hidden until catastrophic damage occurs. Yet the fact that portions of the Acropolis remained functional for centuries suggests that the hydraulic design was highly effective. Perhaps nowhere is the technological mystery more fascinating than in the structure archaeologists designate as Temple A, which is among the most significant discoveries on the Acropolis because it offers clues about a possible system of architectural standardization. Detailed measurements of the foundations reveal recurring dimensions, repeated spacing patterns, and proportional relationships that appear unlikely to be accidental, leading some researchers to propose a provocative possibility that the builders may have employed a modular design system. In modern architecture, modular construction involves creating structures from standardized units governed by predetermined measurements, simplifying planning, improving consistency, and reducing construction errors. And this concept is fundamental to modern engineering and manufacturing. Evidence from Temple A suggests the Etruscans may have applied a similar principle more than 2,000 years ago, as certain foundation dimensions appear to follow recurring ratios. Column spacing may have been derived from a common measurement unit, and structural elements seem organized according to repeatable geometric rules. If this interpretation is correct, the implications are enormous, indicating that Etruscan builders were not merely skilled craftsmen responding to local conditions, but may have possessed an abstract architectural framework capable of generating complex structures through standardized design principles. The mystery lies in the absence of documentation, as no surviving manuals explain the system, no mathematical texts describe the measurements, and no architectural treatises equivalent to those later written by Roman engineer Vitruvius have been discovered. The stones suggest a coherent methodology, yet the methodology itself has vanished, creating one of archaeology's most intriguing paradoxes, in which the physical output survives while the intellectual process behind it remains largely invisible. The stonework itself raises additional questions, as many blocks used throughout Volterra display surprisingly precise workmanship with tool marks indicating systematic cutting techniques, surfaces prepared with consistency, and joints often fitting closely despite the absence of modern machining equipment. Experimental archaeologists attempting to replicate ancient stoneworking methods frequently encounter an uncomfortable reality, as even with access to modern understanding of materials and mechanics, reproducing ancient craftsmanship using period-appropriate tools can be extraordinarily labor-intensive. The issue is not whether ancient workers could achieve such results, as clearly they did, but whether they possessed organizational methods, workforce management systems, and construction procedures more advanced than traditionally assumed. In the hills of Tuscany, Italy, lie the ruins of Vetulonia, an ancient Etruscan city where enormous tombs, advanced metallurgy and sophisticated engineering emerged centuries before Rome dominated the Mediterranean. More than 2,500 years later, archaeologists can still see the results of its technology, but many of the methods behind it remain a mystery. Although known from ancient historical references, the true location of Vetulonia was lost for centuries. In the 19th century, archaeologist Isidoro Falci identified the site through systematic excavations that uncovered monumental tombs, rich grave goods, defensive walls, and evidence of a once powerful urban centre. What emerged from the soil was not merely a forgotten city, but one of the most technologically sophisticated settlements of the Etruscan world. The rise of Vetulonia was closely connected to one of the most important technological revolutions of the ancient Mediterranean, metallurgy. The city occupied a strategic position near the mineral-rich regions of southern Tuscany and maintained access to the iron deposits of Elba Island. Archaeological excavations have revealed weapons, tools, bronze vessels, jewelry, and industrial debris, indicating large-scale metal production. This alone is not surprising, as many ancient societies worked with metal, but what makes Vetulonia unusual is the consistency and quality of its products. Modern metallurgical analysis has shown that many Etruscan bronze artifacts contain carefully controlled proportions of copper and tin, requiring not only access to raw materials, but also a practical understanding of furnace behavior, temperature management, and alloy composition. Without thermometers, chemical laboratories, or written technical manuals, Etruscan metalworkers repeatedly produced durable alloys whose mechanical properties rivaled those of many contemporary cultures. When compared with early Iron Age communities elsewhere in Europe, Vetulonia appears significantly more advanced, with craftsmen operating within complex trade networks that stretched across the Mediterranean, connecting the city to Greek colonies, Phoenician merchants, Sardinia, and perhaps even regions farther east. Yet, despite the abundance of finished products, the manufacturing knowledge itself has largely vanished. Archaeologists can analyze the metal, but they cannot fully reconstruct the expertise that produced it. The most astonishing mystery of Vetulonia rises above the landscape in the form of gigantic tumulus tombs. Some of these burial monuments exceed 60 meters in diameter and contain internal chambers constructed from carefully arranged stone blocks, with famous examples such as the Tomb of the Pietrera and the Tomb of the Diavolino, demonstrating engineering capabilities that seem remarkably sophisticated for the period. At first glance, these structures appear simple, essentially giant artificial hills covering burial chambers, but the reality is far more complicated. A mound 60 meters wide can contain tens of thousands of tons of earth and stone, generating enormous pressure on the chambers beneath it. If the internal supports are insufficient, the roof collapses. If drainage is poorly designed, water infiltration weakens the structure, and if the foundation shifts, the entire monument may fail. Yet many of these tombs have survived for more than 25 centuries. Modern engineers recognize that maintaining the stability of such a system requires an understanding of load distribution and soil behavior, meaning the builders needed to predict how weight would move through the structure, prevent water accumulation, and ensure that the burial chambers remained stable beneath an artificial mountain. The mystery deepens when considering the available technology, as no steel reinforcement, concrete computer modeling, or modern geological surveys existed, yet the tombs remain standing. Comparable challenges can be seen in the burial monuments of Mycenaean Greece and the tumulus traditions of Northern Europe. But the Etruscan examples occupy a unique position, with their combination of scale, geometry, and longevity suggesting an empirical understanding of structural engineering that was never formally recorded, leaving the question of how this knowledge was acquired unanswered. Another puzzle emerges from the stone architecture itself, as many blocks used in Vetulonia's tombs and defensive structures display surprisingly accurate fitting. Although not as extreme as the polygonal masonry of Sacsayhuaman in Peru or the walls of Alatri in central Italy, the precision remains impressive. Researchers studying tool marks have identified evidence of systematic stone shaping, with builders repeatedly achieving straight surfaces, controlled angles, and stable joints despite working with relatively simple iron tools. The challenge becomes clearer from an engineering perspective, as producing a flat stone surface several meters long is difficult even today, without proper measuring equipment, and maintaining geometric consistency across dozens or hundreds of blocks requires reliable standards of measurement. Yet no complete Etruscan technical texts describing surveying procedures have survived, leaving the buildings intact while the instruction manuals have disappeared. Excavations have gradually revealed that Vetulonia was not merely a collection of buildings scattered across a hillside, but a city that exhibits clear evidence of planning. Roads connect strategic sectors, residential zones interact with defensive structures, water management systems appear integrated with the surrounding terrain, and access routes were designed to exploit natural topography while maintaining communication throughout the settlement. This suggests organized surveying, as ancient surveyors faced the difficult task of measuring slopes, establishing alignments, calculating distances, and maintaining orientation across uneven ground, where even small errors could create serious problems for drainage systems, roads, and defensive walls. Although the Romans later became famous for such capabilities, Vetulonia demonstrates that sophisticated surveying traditions may already have existed among the Etruscans, raising unanswered questions about how accurate those methods were and how the knowledge was transmitted between generations. One of the least discussed mysteries of Vetulonia concerns water management, as every ancient city depended on controlling water, with excess rainfall capable of destroying roads, weakening foundations, and triggering erosion, while insufficient water threatened agriculture and daily life. The surrounding landscape of Vetulonia presented additional challenges due to its historical marshes and changing coastal environments. Archaeological evidence suggests that the inhabitants successfully adapted to these conditions, with drainage systems, road placement, and settlement planning appearing carefully coordinated. Modern hydrological studies show that even small mistakes in drainage design can produce catastrophic long-term damage, yet portions of the urban infrastructure survived for centuries, raising the fascinating possibility that ancient engineers possessed a practical environmental knowledge far more sophisticated than commonly assumed. What do you think? Did the engineers of Vetulonia possess practical knowledge far beyond what we currently understand, or have we simply lost the records that would explain their achievements? Share your thoughts in the comments below. Perched in the Andes of southern Peru at an elevation of more than 3,500 meters above sea level, Vilcashuaman is often seen as just another ancient Inca ruin. Yet among its stone terraces stands a massive ceremonial platform known as the ushnu, a structure so precisely integrated into the landscape that archaeologists still debate how it was designed, surveyed, and constructed without modern instruments. Following the Spanish conquest in the 16th century, much of Vilcashuaman was dismantled and built over. Colonial churches rose directly on top of Inca foundations. Archaeological investigations conducted during the 19th and 20th centuries gradually revealed that beneath the colonial town survived one of the most important provincial capitals of the Inca Empire. What emerged was not merely a settlement. It was a carefully planned administrative centre positioned along the vast royal road system known as the Capac-Nan, connecting Cusco with distant regions of the empire. The first mystery begins with the city's layout itself. Vilcashuaman occupies rugged mountainous terrain where construction is naturally difficult. Modern engineers facing such conditions would first perform topographic surveys, calculate slope stability, establish reference points, and create detailed maps before beginning construction. The Inca possessed none of these technologies in a modern sense. No compasses, no steel measuring instruments, no theodolites, and no written engineering manuals. Yet the city displays remarkable organization. Roads converge towards central ceremonial spaces. Major structures align with one another across uneven terrain. Terraces, retaining walls, plazas, and ceremonial architecture function as components of a unified design rather than isolated buildings. Researchers have long questioned how Inca planners achieved this level of spatial control. Similar questions arise at Machu Picchu, Ollantaytambo, and Sacsayhuaman, but Vilcashuaman presents a unique challenge because its urban design appears to combine administrative, ceremonial, and astronomical functions within a relatively compact area. Modern archaeological mapping suggests intentional geometric planning rather than gradual organic growth. The settlement appears to have been conceived as a complete project before construction began. If true, the planners possess surveying capabilities far more sophisticated than traditionally assumed. At the heart of the site stands the structure that continues to fascinate archaeologists more than any other, the ushnu. Rising in a series of massive stone terraces, the monument dominates the surrounding landscape. Today it resembles a stepped pyramid, but that description barely captures its complexity. The word ushnu appears throughout the Inca world. Historical records describe ceremonial platforms used by rulers for rituals, political gatherings, astronomical observations, and state administration. Yet the Vilcashuaman ushnu is among the largest and most impressive examples ever constructed. This immediately creates a problem. If the structure was merely ceremonial, why invest such extraordinary resources into its construction? Transporting stone blocks to an elevation exceeding 3,500 meters required enormous labor. Building terraces capable of supporting large gatherings demanded advanced understanding of load distribution and foundation stability. Maintaining geometric consistency throughout multiple levels required precise planning. The scale appears excessive for a simple ceremonial stage. Some researchers suggest the ushnu functioned as a symbolic model of the Inca cosmos. Others argue it served as an administrative command center, where imperial authority was displayed before regional populations. A more intriguing possibility involves astronomy. Across the Andes, many ceremonial structures exhibit alignments with solar events such as solstices and equinoxes. Several investigations have suggested that ushnus may have acted as observation platforms linked to calendrical calculations. If the Vilcashuaman ushnu performed such a role, then its dimensions, orientation, and position may have been determined by celestial observations accumulated over generations. The challenge is that definitive proof remains elusive. Archaeologists can measure the monument, reconstruct its geometry, and model sightlines using modern software. What they cannot fully recover is the intellectual process that originally guided its design. The giant ushnu remains one of the clearest examples of a structure whose physical form survives while its engineering logic has largely vanished. Another mystery lies in the stonework itself. Like many elite Inca structures, parts of Vilcashuaman display finely fitted masonry. Individual stones interlock with extraordinary accuracy despite the absence of mortar. The joints between blocks often appear astonishingly tight. This achievement becomes even more remarkable when compared with construction methods elsewhere in the ancient world. The Egyptians used large limestone blocks, but relied heavily on gravity and mass. The Romans frequently employed mortar to compensate for irregularities. Medieval builders often concealed imperfections beneath plaster. The Inca pursued a different solution. They shaped stones so precisely that neighbouring blocks effectively locked together. Experimental archaeology has attempted to replicate this process using stone hammers and abrasive materials. The results demonstrate that such precision is possible. However, achieving it consistently across large structures requires immense labour and exceptional craftsmanship. The unanswered question is efficiency. How did Inca builders produce such accuracy on a scale large enough to construct entire administrative centres? No surviving records describe the exact workflow. No detailed construction manuals have been found. The techniques were evidently effective, yet the knowledge system behind them remains largely invisible. Peru sits along one of the most seismically active regions on Earth. Major earthquakes have repeatedly struck the Andes throughout recorded history. Despite this reality, many Inca structures have survived remarkably well. Vilcashuaman offers valuable clues. Walls frequently lean slightly inward. Doorways often adopt trapezoidal shapes. Stone blocks interlock in ways that permit limited movement during seismic activity. Modern structural analysis indicates that these characteristics can improve earthquake resistance. The mystery is not whether the system works. The mystery is how the Inca discovered it. No mathematical theory of seismic engineering existed. No modern geological science existed. Yet repeated architectural solutions appear throughout the empire. Some researchers argue that centuries of accumulated experience gradually refined construction methods through observation and adaptation. Others believe the consistency across distant regions implies a more organized transfer of engineering knowledge. Either explanation raises further questions about how technical expertise was preserved and communicated across an empire stretching thousands of kilometers. Vilcashuaman's construction may be even more remarkable than its design. Massive stone blocks were quarried, transported, and assembled in rugged mountains without modern machinery. The Inca had no wheeled transport or powerful draft animals. Although llamas carried small loads, large-scale construction relied mainly on human labor. Like Machu Picchu, Ollantaytambo, and Sacsayhuaman, Vilcashuaman demonstrates how Inca engineers achieved extraordinary results with simple tools. The mystery is not that it was built, the evidence is clear, but how such an effective logistical system made it possible. What do you think? Was the giant ushnu primarily a ceremonial monument, an astronomical observatory, a political command center, or something else entirely? Share your theory in the comments below. In the volcanic valleys of southern Tuscany, Italy, lies Savannah, a place where ancient engineers cut roads directly into solid rock so deeply and so precisely that even modern archaeologists still debate how they achieved it more than 2,000 years ago. Although the settlement itself was known throughout history, systematic archaeological investigation accelerated during the 19th and 20th centuries when researchers began documenting the vast Etruscan necropolis surrounding Savannah. What initially appeared to be a collection of tombs soon revealed something far more extraordinary: an immense network of sunken roads, monumental rock-cut architecture, and engineering works carved directly into volcanic stone. What archaeologists discovered was not merely a cemetery, it was an engineered landscape. The ancient Etruscans flourished in central Italy between roughly the 8th and 3rd centuries BCE, long before Rome became the dominant power of the Mediterranean. Many ancient civilizations built monuments. The Egyptians built pyramids, the Greeks built temples, and the Romans built aqueducts. The Etruscans at Savannah appear to have done something different. Rather than placing structures onto the landscape, they transformed the landscape itself. Across the valleys surrounding Savannah, researchers have identified numerous rock-cut tombs connected by an extensive system of excavated corridors known as V-cave. These passageways were not simply carved into existing cracks or ravines. In many locations, they were deliberately excavated through solid volcanic tuff, creating vertical walls that rise 10 to 20 meters above the pathways below. Standing inside one of these corridors feels less like walking through a road and more like moving through a gigantic artificial canyon. The scale alone raises questions. Thousands of cubic meters of stone had to be removed, every wall had to remain stable, every route had to maintain usable gradients, and all of this was accomplished without explosives, steel tools, engines, cranes, or modern surveying equipment. Among all the unanswered questions surrounding Savannah, perhaps none is more fascinating than the apparent sophistication of Etruscan surveying. Modern engineers understand how difficult it is to establish long, consistent alignments across uneven terrain, and today we rely on total stations, GPS receivers, laser scanners, satellite imagery, and digital terrain models. The builders of Savannah possessed none of these technologies, yet many V-cave display remarkable directional consistency. Researchers studying Etruscan landscapes have noted that these routes frequently maintain logical connections between settlements, agricultural zones, sacred areas, and necropolises, appearing integrated into a larger regional plan rather than being created randomly over time. This creates a difficult question. How did Etruscan engineers determine where to excavate? To carve a corridor through solid rock, surveyors must first establish a route, estimating elevation changes, drainage behavior, geological stability, and future usability, where any major error could multiply into thousands of hours of wasted labor. Even a deviation of a few degrees could dramatically alter the final path, yet many of these corridors follow terrain with impressive efficiency. Some researchers suggest that the Etruscans employed sophisticated geometric surveying methods using ropes, sighting poles, plumb lines, and astronomical observations, while others believe generations of accumulated practical experience allowed them to achieve surprising accuracy. The problem is that no surviving technical manuals explain their procedures. The roads survive, but the calculations do not. The engineering challenge becomes even more impressive when considering the sheer amount of material removed. A typical V-cave may extend hundreds of meters while reaching heights of 10 to 20 meters, and even conservative estimates suggest that many thousands of tons of rock were excavated. For comparison, modern construction projects involving comparable volumes would normally employ hydraulic excavators, drilling equipment, dump trucks, and laser-guided surveying systems. The Etruscans relied primarily on human labor. Archaeologists have identified tool marks on various rock surfaces, demonstrating systematic excavation techniques, yet the exact organization of labor remains unclear. Questions persist. How many workers participated? How long did individual corridors require? How was debris removed from narrow excavation zones? And where was the excavated stone deposited? Surprisingly, answers remain incomplete. The physical evidence proves the work occurred, but the logistics remain elusive. The volcanic tuff underlying Savannah is relatively soft when freshly exposed, but becomes more durable after weathering, a property that undoubtedly aided excavation. However, it does not fully explain the survival of the corridors. Many walls remain standing after more than 2 millennia, suggesting that the builders understood far more about geology than is often assumed. When modern engineers cut into slopes, they analyze fracture systems, water infiltration, slope stability, load distribution, and erosion potential, as mistakes can trigger collapses. The Etruscans apparently achieved large-scale excavations while avoiding catastrophic structural failures across much of the landscape. This raises an intriguing possibility. Perhaps ancient builders possessed extensive empirical geological knowledge acquired through generations of quarrying, mining, and construction. They may not have possessed geological science in the modern sense, but they may have understood the behavior of local rock formations with extraordinary practical precision, and the surviving corridors themselves may be evidence of that expertise. One of the most overlooked mysteries of Savannah involves water. At first glance, the V-cave appear vulnerable. Deep trenches should collect rainfall, standing water should accelerate erosion, and seasonal flooding should damage the corridors. Yet many remain surprisingly stable. Researchers have identified drainage features integrated into various sections of the landscape, where subtle gradients encourage runoff and natural channels appear incorporated into broader designs. In some locations, erosion seems far less severe than expected given the age of the structures. The situation resembles challenges encountered at sites such as Machu Picchu, Petra, and the underground cities of Cappadocia, where water management appears inseparable from architectural survival. Without effective drainage, none of these sites should have endured for centuries. Savannah belongs within this same category of ancient engineering puzzles, and its builders seem to have understood hydrology well enough to protect massive, excavated features across extremely long periods of time. The tombs of Savannah introduce another layer of complexity. The most famous example, the tomb of Ildebranda, resembles a classical temple emerging from a hillside. What makes this structure remarkable is the method of construction. The builders did not assemble columns and walls from separate blocks, but instead removed the surrounding rock, meaning everything visible today was created by subtraction. Columns, stairways, chambers, decorative elements, and architectural facades were all carved from a single geological mass. This process required extraordinary planning, as a mason assembling blocks can replace damaged components, but a rock-cut architect cannot, and one major mistake can destroy years of work. Similar challenges appear at Petra in Jordan, the rock-cut churches of Lalibela in Ethiopia, and India's Kailasa temple. Yet Savannah remains distinctive because such techniques were applied across an entire funerary landscape rather than a single isolated monument. What do you think was the true purpose of the giant V-cave corridors of Savannah? Transportation, ritual processions, astronomical design, or something we still haven't discovered? Share your theory in the comments below. Overlooking the plains of northeastern Spain, about 30 kilometers from the Mediterranean coast in modern Catalonia, lie the ruins of Olstret, the largest known Iberian city ever discovered. At first glance, it appears to be another Iron Age settlement, a collection of stone walls, towers, streets and houses dating back more than 2,000 years. Yet the more archaeologists study Olstret, the more difficult questions emerge. How did a society without modern mathematics, steel machinery, written engineering manuals, or advanced surveying instruments construct a fortified urban centre capable of supporting thousands of inhabitants? And why do some of its engineering achievements seem far more sophisticated than traditionally expected for the Iberian peoples of pre-Roman Europe? The site was first identified through archaeological investigations during the 20th century, revealing the remains of a major settlement occupied between approximately the 6th and 2nd centuries BCE. excavations uncovered an urban area covering more than 15 hectares, protected by massive fortifications and organized according to a level of planning that surprised researchers. What initially appeared to be a regional stronghold gradually revealed itself as one of the most technically impressive urban centers of ancient Iberia. One of the greatest mysteries begins with the city's location. Olstret was built on elevated terrain that provided defensive advantages, but also created serious engineering challenges. Constructing a large settlement on uneven hillsides requires far more than simply placing stones on the ground. Builders must understand slope stability, drainage, foundation behavior, and the movement of water during seasonal storms. Modern engineers solve these problems using topographic surveys, mathematical modeling, and geotechnical analysis. The inhabitants of Olstret possessed none of these tools, yet the city remained functional for centuries. Archaeological evidence suggests that significant portions of the settlement were carefully adapted to the natural landscape rather than simply imposed upon it. Terraces were created, foundations were adjusted to varying elevations, and urban spaces were organized in ways that minimized instability. This raises an important question. Were Iberian builders relying solely on accumulated experience? Or had they developed practical engineering principles that have been lost to history? The absence of surviving technical documents makes it difficult to determine how much of their knowledge was formalized. The city's fortification system presents an even more intriguing puzzle. Massive defensive walls surrounded the settlement, incorporating towers and gateways strategically positioned to maximize protection. Some sections of these walls reach several meters in thickness, requiring enormous quantities of stone and labor. Researchers estimate that the construction of such fortifications would have demanded the extraction, transportation, and placement of thousands of tons of material. Today, moving stone on this scale requires cranes, trucks, hydraulic equipment, and detailed planning software. The people of Olstret possessed none of these technologies. Instead, they relied entirely on human labor, simple tools, and organizational systems that remain only partially understood. Archaeologists can identify the finished structures, but reconstructing the exact logistics behind their construction remains difficult. This challenge is not unique to Olstret. Similar questions arise at sites such as Machu Picchu in Peru, where Inca builders transported and assembled enormous stones in mountainous terrain, and at Sacsayhuaman, where some blocks exceed 100 tons. The scale at Olstret was smaller, yet the underlying mystery remains remarkably similar. How did ancient societies consistently organize labor and resources on a scale that appears disproportionate to the technological tools available to them? Another unresolved question involves surveying accuracy. Defensive walls are most effective when positioned according to precise knowledge of terrain. Towers must cover potential blind spots. Gateways must be located where they can be defended efficiently. Lines of sight must be maintained between strategic positions. Modern military engineers calculate these factors using maps, geometry, and computer simulations. At Olstret, the placement of defensive features often appears remarkably rational. Certain towers command broad views of surrounding approaches, while critical sectors of the landscape are monitored from elevated positions. Whether this reflects sophisticated surveying techniques or generations of accumulated practical experience remains uncertain. Water management introduces another layer of mystery. The city was not located directly beside a major river capable of supplying a large urban population. Nevertheless, archaeological excavations have revealed cisterns, storage facilities, and systems designed to collect and manage water resources. For a settlement potentially housing several thousand inhabitants, maintaining reliable access to water would have been essential. This challenge becomes even more impressive when considering climate variability. Mediterranean environments experience seasonal fluctuations in rainfall. Engineers responsible for water storage must estimate consumption, evaporation, and future needs. Modern cities use hydrological models and statistical data. The inhabitants of Olstret relied on observation and experience. Researchers continue debating how sophisticated these systems truly were. Some argue that practical trial and error over centuries could explain their effectiveness. Others suggest that the scale of planning visible at the site implies a deeper understanding of environmental management than traditionally assumed. Similar debates occur at Petra in Jordan, where Nabatean engineers developed elaborate systems to control water in an arid landscape, and at ancient Roman cities where hydraulic infrastructure reached extraordinary levels of complexity. Urban organization presents another fascinating puzzle. Excavations indicate that streets, residential areas, storage spaces, and defensive structures were arranged according to coherent patterns rather than a random growth. This observation challenges older assumptions that Iron Age settlements expanded in a largely organic manner. In modern urban planning, organized layouts improve transportation efficiency, security, drainage, and social administration. The more researchers examine Olstret, the more they encounter evidence suggesting that urban space was deliberately structured. Yet no surviving Iberian texts explain the principles behind these decisions. The problem becomes particularly striking when compared with other ancient civilizations. At Marzabotto in Etruscan Italy, archaeologists discovered a city built according to a carefully planned grid. At Mohenjo-Daro in the Indus Valley, standardized urban design appeared more than 4,000 years ago. At Teotihuacan in Mexico, entire districts were organized around geometric planning principles. Olstret does not reach the same scale, but it belongs to a broader global pattern in which ancient societies repeatedly demonstrate levels of planning that seem surprisingly advanced for their era. Perhaps the most overlooked mystery concerns communication and regional coordination. Olstret was not an isolated settlement. It functioned within a network of Iberian communities distributed across northeastern Iberia. From its elevated position, parts of the surrounding landscape remain visible for great distances. Some researchers have proposed that visual signaling systems may have connected multiple settlements. Fire beacons, smoke signals, or reflected sunlight could theoretically transmit information across considerable distances. Comparable systems are known from later civilizations, including Roman military frontiers and medieval watchtower networks. Direct evidence for such communication at Olstret remains limited, yet the strategic placement of certain defensive positions continues to provoke debate. In the rolling landscape of northwestern Spain, about 23 kilometers northeast of Lugo, in Galicia, lies Castro de Viladonga, one of the best preserved Iron Age hill forts in Europe. Today it appears as a collection of stone foundations surrounded by earthworks. But beneath this seemingly modest archaeological site lies a technological puzzle that continues to challenge researchers. Excavations revealed a fortified settlement occupied primarily between the 1st and 5th centuries CE, during a period when indigenous Celtic traditions interacted with the expanding influence of Rome. Yet the deeper archaeologists investigate Viladonga, the more difficult it becomes to explain how its builders achieved such sophisticated results using technologies that should have been relatively simple. The site was first recognized by scholars in the early 20th century, but systematic excavations beginning in the 1970s transformed understanding of the settlement. What emerged from beneath centuries of soil was not an isolated village, but a carefully organized fortified community occupying roughly 4 hectares. Multiple defensive circuits, strategically positioned ditches, complex residential districts, drainage systems, workshops, and evidence of long-distance trade suggested a society possessing a far more advanced understanding of engineering and environmental management than previously assumed. The first mystery appears before one even enters the settlement. Castro de Viladonga occupies a naturally elevated position, approximately 550 meters above sea level. At first glance, the choice seems obvious. Higher ground offers visibility and defense. Yet modern topographic analysis reveals that the location provides an unusually effective balance between visibility, access to water, agricultural potential, and defensive control. The hill dominates surrounding routes while remaining close to fertile valleys, capable of supporting a substantial population. Such positioning may sound simple, but military planners today rely on detailed mapping, elevation models, and geographic information systems to identify locations with similar advantages. The builders of Viladonga possessed none of these tools. Nevertheless, they selected a position that optimized nearly every strategic variable. Archaeologists continue debating whether this resulted from generations of accumulated experience or from a surveying tradition whose methods have disappeared entirely. Approaching the settlement reveals another challenge. Viladonga is protected by multiple concentric defenses consisting of ramparts, walls, and ditches. The outer defensive system follows the contours of the hill with remarkable consistency. Rather than forcing geometry onto the landscape, the builders adapted their fortifications to the terrain itself. This distinction is important. Modern engineering recognizes that working with natural topography often produces greater structural stability than attempting to reshape it completely. Similar principles appear at Machu Picchu in Peru, where Inca engineers integrated architecture into mountain slopes, and at the Iron Age hill forts of Britain, where defensive earthworks exploit natural contours. Yet Viladonga demonstrates a level of adaptation that raises uncomfortable questions about how much practical knowledge Iron Age engineers possessed. The geometry of the fortifications appears especially intriguing. Archaeologists have measured recurring patterns in wall placement and defensive spacing. While not mathematically perfect, the layout repeatedly achieves effective defensive coverage while minimizing construction effort. Every meter of wall required labor, stone, and maintenance. Building unnecessarily large defenses would have wasted precious resources. Building defenses too small would have endangered the settlement. Somehow, the builders consistently achieved a balance that modern military engineers would recognize as rational optimization. Equally mysterious is the question of construction itself. Thousands of tons of stone had to be extracted, transported, positioned, and stabilized. Unlike Roman builders, the inhabitants of Viladonga left behind no engineering treatises, no construction manuals, and no technical diagrams. Yet the surviving structures demonstrate a practical understanding of load distribution and structural durability. Comparisons with larger ancient monuments are revealing. At Sacsayhuaman in Peru, researchers marvel at the precision of massive stone blocks. At the Great Pyramid of Giza, they debate logistics and alignment. Viladonga operates on a smaller scale, but the underlying challenge remains similar. How does a pre-industrial society repeatedly organize labor, materials, and engineering knowledge without written technical documentation? The mystery deepens when examining water management. Galicia receives substantial rainfall throughout the year. For any fortified settlement, water represents both a necessity and a threat. Excess water can destabilize foundations, erode defensive earthworks, and damage structures. Excavations suggest that Viladonga incorporated subtle but effective drainage solutions. Surface gradients directed water away from critical areas. Defensive ditches may have served multiple purposes, functioning not only as obstacles, but also as elements of water control. Certain pathways appear designed to minimize erosion despite centuries of exposure to rainfall. Today, engineers model hydrological behavior using computer simulations. The inhabitants of Viladonga possessed only observation and experience, yet the settlement functioned successfully for generations in a region where poor drainage would have produced catastrophic consequences. The precise methods by which these solutions were developed remain unknown. Inside the fortifications lies another puzzle. The settlement contains dozens of circular and rectangular structures arranged within a surprisingly organized urban framework. Roads, domestic spaces, workshops, and communal areas coexist within a limited area. Many early historians described Iron Age communities as relatively unplanned settlements that expanded organically over time. Viladonga challenges that assumption. The internal arrangement suggests intentional spatial planning. Buildings are positioned in ways that maximize usable space while maintaining circulation routes and access between districts. Modern urban planners understand the difficulty of balancing density, accessibility, defense, and functionality. Yet the residents of Viladonga achieved a practical version of this balance nearly 2,000 years ago. Whether this reflects centralized planning or an inherited tradition of settlement design remains one of the site's most fascinating unanswered questions. Evidence of metallurgy introduces another layer of complexity. Archaeologists have recovered iron tools, bronze objects, ornaments, and manufacturing debris indicating local production and repair activities. Iron metallurgy is not a simple craft. Producing useful iron requires controlling temperatures exceeding 1,000 degrees Celsius, managing airflow, selecting appropriate ores, and understanding how different conditions affect the final material. Without thermometers, chemical theory, or modern furnaces, ancient metallurgists nevertheless achieved results sufficient to support agriculture, construction, and defense. Similar mysteries surround iron production throughout Iron Age Europe, but Viladonga provides a particularly vivid example because the settlement's survival depended upon maintaining these technologies over long periods. Scientific analysis of recovered artifacts demonstrates that the inhabitants were not isolated. Imported materials and Roman goods indicate participation in regional trade networks extending across northwestern Iberia and beyond. This raises another unresolved question. How did technological knowledge spread across ancient Europe? Ideas concerning construction, metallurgy, agriculture, and defense appear repeatedly across distant settlements. Information clearly moved from one region to another, yet historians still struggle to reconstruct the mechanisms responsible. Without formal educational institutions, printed manuals, or centralized bureaucracies, technological traditions somehow propagated across hundreds of kilometers. Perhaps the most intriguing mystery concerns standardization. Many structures exhibit recurring construction techniques and architectural patterns. Consistency implies shared rules. In modern engineering, standards reduce errors and ensure compatibility. They allow builders working on different projects to produce predictable results. At Viladonga, physical evidence suggests comparable concepts may have existed. Builders repeatedly employed similar solutions to recurring problems, yet no written standards survive. Archaeologists can observe the outcomes, but cannot identify the instructions that generated them. Castellar de Meca sits on a rocky plateau overlooking the valleys of eastern Spain, near modern-day Ayora in the province of Valencia, and at first glance it appears to be little more than a forgotten hilltop settlement. Yet when archaeologists began studying the site in detail, they realized they were looking at something far more extraordinary. Spread across roughly 10 hectares and occupied primarily during the Iberian period, between the 5th and 1st centuries BCE, the settlement preserves one of the most unusual examples of ancient engineering in Western Europe. Unlike many ancient cities where walls and buildings dominate the landscape, Castellar de Meca's greatest achievement lies in the mountain itself. Roads, reservoirs, storage areas, drainage systems, and defensive features were carved directly into solid bedrock, creating a technological landscape whose full purpose and construction methods remain only partially understood. The discovery of the site did not immediately reveal its significance. Early investigators focused on visible structures and defensive walls, assuming Castellar de Meca was simply another fortified Iberian settlement. Only later did systematic surveys reveal the true scale of the engineering works. Researchers found an extensive network of roads cut directly into limestone, some preserving wheel ruts so deep and regular that they remain visible more than 2,000 years later. These features transformed Castellar de Meca from an archaeological curiosity into one of the most important examples of ancient landscape engineering in the Iberian Peninsula. The most famous mystery concerns the road system itself. Throughout the settlement, deep parallel grooves cut into bedrock mark the paths once travelled by carts. Some ruts exceed 0.5 metre in depth. Archaeologists generally interpret them as the result of centuries of traffic, yet this explanation raises difficult questions. In many locations, the grooves appear remarkably regular, maintaining consistent spacing and alignment across uneven terrain. Such precision suggests that at least portions of the network may have been intentionally engineered, rather than simply worn into existence through repeated use. If these routes were deliberately planned, the implications are significant. Ancient engineers would have needed to calculate gradients, turning radii, drainage requirements, and traffic flow long before Roman road-building techniques became dominant in the region. The challenge becomes even more impressive when considering the terrain. Castellar de Meca sits atop a naturally defensive mountain environment where movement is constrained by steep slopes and exposed rock surfaces. Designing a transportation system capable of moving goods efficiently through such conditions would have required sophisticated practical knowledge of surveying and logistics. Comparisons with other ancient engineering centres highlight the puzzle. At Petra in Jordan, Nabatean engineers carved roads, water channels, and monumental facades directly into sandstone cliffs. At Machu Picchu in Peru, Inca builders reshaped entire mountainsides through terracing and carefully planned pathways. Castellar de Meca operated on a smaller scale, yet the underlying challenge was similar. In each case, engineers chose not merely to build upon a landscape, but to transform the landscape itself into an integrated technological system. Water management introduces another layer of mystery. The settlement occupies a high rocky plateau where access to permanent freshwater sources would have been limited. Yet archaeologists have documented numerous cisterns, reservoirs, channels, and collection basins carved directly into the bedrock. These installations were designed to capture and store seasonal rainfall, creating a sustainable water supply capable of supporting a substantial population. What remains uncertain is how the system was planned. Effective rainwater harvesting requires careful calculations involving catchment areas, seasonal precipitation patterns, storage capacity, evaporation rates, and overflow management. Modern hydrological studies demonstrate that even small errors in gradient can significantly reduce collection efficiency. Nevertheless, many of the reservoirs at Castellar de Meca continue to function today, demonstrating a level of engineering durability rarely associated with Iron Age societies. This raises an important question. How much mathematical and environmental knowledge did the builders possess? No surviving Iberian engineering manuals explain the design process. Archaeologists can measure the structures, estimate capacities, and reconstruct water flows, but the intellectual framework behind the system remains invisible. The engineers themselves left almost no written record explaining how these solutions were developed. Equally intriguing is the enormous amount of rock that had to be removed. Every road, reservoir, storage platform, stairway, and defensive feature required excavation directly into limestone bedrock. While no precise calculation exists for the total volume extracted, the cumulative quantity is substantial. The labour investment would have been immense, especially considering the technological limitations of the period. The Iberians possessed iron tools, but they lacked steel machinery, explosives, hydraulic drills, or mechanised excavation equipment. Yet they succeeded in reshaping large portions of an entire mountain. Similar questions arise at sites such as the rock-cut churches of Lalibela in Ethiopia and the cave complexes of Ellora in India. In each case, archaeologists can identify the finished product but struggle to reconstruct the exact methods used to achieve it. The organisation required for such a project may be even more impressive than the physical construction itself. Excavation on this scale implies coordinated labour, resource management, long-term planning, and centralised authority. Workers would have needed food supplies, tool production, maintenance systems, and logistical support. The settlement, therefore, appears not merely as an engineering achievement, but as evidence of a highly organised society capable of managing complex projects over extended periods. Another unresolved mystery concerns the purpose of many carved features scattered throughout the site. Numerous depressions, platforms, and enclosed spaces remain difficult to interpret. Some researchers propose they functioned as storage facilities for agricultural products. Others suggest they served commercial activities, military logistics, or specialized industrial processes. Certain arrangements appear almost modern in their efficiency, leading some archaeologists to describe parts of Castellar de Meca as resembling an ancient transport hub. The site's defensive characteristics add further complexity. Positioned high above surrounding valleys, Castellar de Meca commanded extensive views of regional trade routes. Defensive walls, controlled access points, and naturally protected approaches indicate that security played an important role in the settlement's design. Yet the infrastructure inside the site often appears optimized for economic activity rather than purely military purposes. This dual character has fueled ongoing debate. Was Castellar de Meca primarily a fortress, a trading center, an administrative hub, or a combination of all three? On a rocky hill overlooking the Mediterranean coast near modern-day Alicante, Spain, lies Tossal de Manises, the archaeological remains of ancient Lucentum. Today, visitors see weathered walls, fragmented streets, and scattered foundations. Yet beneath these ruins lies a puzzle that continues to challenge archaeologists. More than 2,000 years ago, builders transformed a strategic coastal ridge into a fortified urban centre that controlled trade routes, monitored maritime traffic, managed water resources, and defended itself against invasion. The city was not enormous by Roman standards, but what makes Tossal de Manises remarkable is the sophistication hidden within its design. The surviving stones suggest a level of planning, surveying, and engineering that appears surprisingly advanced for its era, while many of the technical methods behind its construction remain only partially understood. The site became widely recognized through archaeological excavations conducted during the 20th century, although references to ancient remains had existed much earlier. Located approximately 3 kilometers northeast of Alicante's historic center, the settlement occupied a naturally elevated position overlooking the Bay of Alicante. From this vantage point, inhabitants could observe approaching ships, monitor commercial activity, and defend one of the most strategically valuable stretches of coastline in southeastern Iberia. Archaeological evidence indicates that the settlement evolved from an Iberian community before becoming integrated into the Roman world. What researchers discovered beneath centuries of accumulated soil was not merely a collection of buildings, but a carefully organized urban system. The first mystery begins with the location itself. Modern geographic analysis demonstrates that Tossal de Manises occupies an exceptionally advantageous position. The hill provides visibility across large sections of the coastline while remaining close to Agros-Rasis agricultural land, freshwater sources, and maritime routes. Such a combination would be considered ideal even by modern urban planners. Today, geographic information systems can model visibility, transportation efficiency, and defensive advantages using powerful computers. Ancient builders possessed none of these technologies, yet they selected a site whose strategic characteristics remain impressive more than 2 millennia later. Whether this choice emerged from generations of accumulated local knowledge or from sophisticated surveying practices remains uncertain. The layout of the city introduces another fascinating puzzle. Excavations reveal evidence of organized streets, residential districts, public spaces, and defensive structures arranged according to coherent planning principles. Urban planning of this kind requires far more than simply constructing buildings wherever space is available. Streets must align with terrain. Drainage must function across multiple elevations. Defensive walls must integrate with the natural landscape. Every major structure must fit within a larger system. Archaeologists studying Lucentum frequently note the presence of recurring spatial patterns, suggesting that surveyors worked according to standardized measurements and predetermined plans. This raises an important question. How precise were ancient surveyors? Roman engineers are known to have employed instruments such as the groma for establishing straight lines and right angles. However, the surviving evidence at Tossal de Manises suggests a degree of consistency that still impresses modern researchers. Even small measurement errors become magnified when repeated across an entire city. Yet many sectors of the settlement display remarkable organization. Similar challenges appear at Roman colonial cities throughout the Mediterranean, but Lucentum presents an especially interesting case because its planners had to adapt their designs to an irregular coastal ridge rather than a flat plain. Balancing geometric order against difficult terrain requires considerable technical skill. The defensive system presents perhaps the most visually striking engineering mystery. Portions of the city's fortifications reveal a sophisticated understanding of military architecture. Rather than forming a simple enclosure, sections of the walls appear designed to maximize observation and defensive effectiveness. Angled segments, carefully positioned towers, and strategic sightlines suggest deliberate planning. Military engineers throughout history have understood that geometry can be as important as raw strength. A properly placed tower can eliminate blind spots. A carefully angled wall can expose attackers to crossfire. At Tossal de Manises, some of these principles appear centuries before the highly developed bastion systems of the Renaissance. Comparisons with other ancient fortifications are revealing. At sites such as Vilcashuaman in Peru, researchers marvel at stonework precision. At the walls of Avila in Spain, attention focuses on the scale of the defensive circuit. At Tossal de Manises, the mystery centers less on monumental size and more on intelligent integration between architecture and terrain. The city appears designed not simply to resist attack, but to exploit the landscape itself as part of the defensive system. Water management introduces another layer of complexity. Every ancient city depended on reliable control of water. Too little water threatened survival. Too much water threatened infrastructure. Coastal settlements faced additional challenges, including erosion, seasonal rainfall, and drainage across uneven ground. Archaeologists have identified channels, collection systems, and hydraulic features that indicate substantial planning. The remarkable aspect is not merely that these systems existed, but that they functioned effectively within a complicated topographical environment. Hydraulic engineering remains one of the least appreciated achievements of the ancient world. Modern drainage systems rely on precise calculations involving flow rates, gradients, sediment transport, and erosion control. Ancient engineers lacked modern mathematics and computer simulations, yet many Roman and pre-Roman hydraulic systems operated successfully for centuries. Similar mysteries appear at Petra in Jordan, where Nabatean engineers controlled flash floods, and at Machu Picchu, where Inca drainage systems continue functioning after 500 years. Dos Aldemaneses belongs to this broader tradition of ancient hydraulic expertise that often exceeds popular expectations. Another unresolved question concerns construction logistics. Every visible wall required quarrying, transportation, shaping, and placement. The process demanded coordination of labor, materials, and engineering knowledge. Unlike modern construction projects, ancient builders lacked mechanized cranes, powered vehicles, steel machinery, and hydraulic lifting equipment. Nevertheless, large-scale urban construction occurred repeatedly throughout the Mediterranean world. The challenge becomes especially intriguing when examining the durability of surviving structures. Coastal environments are notoriously destructive. Salt carried by sea air accelerates deterioration. Moisture penetrates stone. Temperature fluctuations create stress within building materials. Yet portions of Lucentum's infrastructure survived more than 2,000 years. This longevity raises questions about material selection, masonry techniques, and environmental knowledge. Did builders understand which stone types would best resist marine conditions? Were construction methods refined through centuries of experimentation? Archaeologists can analyze the results, but reconstructing the exact decision-making process remains difficult. Trade networks provide another dimension of the mystery. Excavations have uncovered evidence connecting Lucentum to wider Mediterranean commerce. Goods, materials, and cultural influences arrived from distant regions. Such connections required navigation across open waters without magnetic compasses, GPS systems, radar, or accurate longitude measurements. Ancient mariners relied on celestial navigation, coastal landmarks, prevailing winds, and accumulated experience. Historians continue debating how precise these methods truly were, yet the archaeological record demonstrates repeated success. Trade functioned across hundreds and sometimes thousands of kilometers. The implications extend beyond economics. Long-distance commerce also facilitated the movement of technical knowledge. Engineering methods, architectural concepts, military innovations, and surveying techniques could spread through interconnected trade networks. Some researchers suspect that Lucentum may have benefited from this exchange of expertise, though determining exactly how knowledge traveled remains challenging. In the hills of Galicia in northwestern Spain lies Castro of San Cibrao de Las, one of the largest fortified settlements ever built by the ancient Celtic peoples of Iberia. More than 2,000 years ago, without concrete, steel, compasses, or modern surveying instruments, its builders created a city whose geometry continues to puzzle archaeologists today. The ruins were known locally for centuries, but systematic archaeological investigations began in the 20th century. Excavations gradually revealed something unexpected. This was not a simple hill fort, and beneath the vegetation lay a carefully planned urban centre covering nearly 10 hectares, protected by massive defensive walls and containing hundreds of stone structures. what emerged from the ground was evidence of engineering sophistication far beyond what researchers once expected from Iron Age communities of Atlantic Europe. For generations, historians viewed the peoples of ancient Galicia as relatively small tribal societies organized around local hill forts. Yet San Cibrao de Las challenged that assumption. The settlement occupies approximately 10 hectares, making it one of the largest castros ever discovered in the region, and archaeologists estimate that at its peak it may have housed several thousand inhabitants, a population that required organization, planning, food distribution, water management, defense systems, and construction knowledge on a scale rarely associated with Iron Age northwestern Iberia. Walking through the site today reveals something remarkable, as the city does not appear to have grown randomly but instead shows many parts integrated into a coherent urban design, leading directly to one of the site's greatest mysteries. If the settlement developed gradually over centuries, why does so much of its structure appear intentionally planned? No architectural manuals survive, no engineering drawings have been found, and no written explanation describes how the city was designed. Yet the physical evidence suggests that somebody understood large-scale planning long before Roman influence reached the region. The most intriguing mystery of San Cibrao de Las is its defensive system, as at first glance the walls appear to follow the contours of the hill, but closer examination reveals something far more sophisticated. The fortifications form complex curved patterns, extending hundreds of meters across uneven terrain, and researchers have noted that many sections maintain surprisingly consistent geometric relationships, despite being constructed on sloping ground, which is where the mystery begins. Modern engineers would use aerial surveys, GPS measurements, laser scanners, and digital mapping software to establish such layouts. Yet the builders of San Cibrao de Las possessed none of these technologies, and still the walls demonstrate an impressive degree of spatial control. Maintaining large curved defensive circuits requires more than simply stacking stones, as builders must determine reference points, estimate distances, preserve alignment, and repeatedly verify measurements over long stretches of terrain, where even small errors accumulate and a deviation of only a few degrees can create substantial displacement hundreds of meters later. The challenge becomes even greater when construction occurs on irregular hillsides where visibility is limited and natural obstacles constantly interfere with measurement, and comparisons with other ancient sites highlight the difficulty, since at places such as the British hill fort of Maiden Castle, defensive systems largely follow natural landforms, whereas at San Cibrao de Las the walls exhibit patterns suggesting deliberate geometric organisation rather than purely reactive adaptation to topography. How this was achieved remains uncertain, as archaeologists have proposed the use of ropes, wooden stakes, pacing systems, and simple surveying techniques, which could explain part of the process. Yet what remains difficult to explain is the consistency maintained across such a large fortified settlement, leaving the walls as evidence of planning while the planning methods themselves have vanished. Another mystery concerns construction technology, as most structures at San Cibrao de Las were built using dry stone masonry, with massive quantities of stone carefully assembled without mortar, binding the blocks together. This technique appears deceptively simple, but in reality, dry stone construction requires a deep understanding of structural behavior. Since every stone influences the stability of neighboring stones, weight must be distributed correctly, pressure must travel through the wall in predictable ways, and weak points must be avoided. Modern structural engineers analyze load paths using mathematical models and computer simulations, yet ancient builders possessed neither, and nevertheless portions of these constructions have survived for more than 2 millennia. The durability is remarkable when compared with many modern buildings, as numerous reinforced concrete structures erected during the 20th century have required major repairs after only a few decades, while the stonework of San Cibrao de Las remains standing after roughly 2,000 years of exposure to wind, rain, temperature fluctuations, and biological growth. This longevity raises a fundamental question about how much practical engineering knowledge these builders possessed, as the surviving architecture suggests expertise accumulated through generations, yet the mechanisms through which that knowledge was transmitted remain largely unknown. The entrances to the settlement reveal another layer of sophistication, as ancient fortifications often relied on walls alone. But at San Cibrao de Las, the gateways appear integrated into a broader defensive strategy. Visitors entering the city could not simply move in a straight line, since many access routes forced directional changes, constrained movement through narrow passages, and exposed approaching individuals to observation from elevated positions, features whose significance military historians recognize immediately. Such arrangements slow attackers, reduce momentum, and create predictable movement patterns, and similar principles appear in medieval castles constructed more than 1,000 years later, making the comparison striking. This raises questions about whether the builders discovered these defensive concepts independently, whether they were the result of centuries of warfare experience, or whether they indicate a level of military planning that archaeologists have historically underestimated, though the evidence does not provide definitive answers. Galicia receives significant rainfall throughout the year, and for any settlement occupying elevated terrain, water represents both a resource and a threat, since without effective drainage, erosion gradually destabilizes roads, foundations, and defensive walls, and over decades or centuries unmanaged runoff can destroy entire sections of a settlement. Yet San Cibrao de Las survived, and excavations suggest that the placement of roads, houses, and open spaces may have contributed to controlling water movement throughout the site, with certain pathways following slopes that naturally direct runoff away from critical structures and residential zones, positioned in ways that reduce exposure to concentrated water flow. Although researchers continue to investigate these relationships, the possibility remains that the settlement incorporated a surprisingly advanced understanding of hydrology, and such knowledge would not necessarily have required formal science, as generations of observation could have produced practical expertise, rivaling the effectiveness of much later engineering traditions. Overlooking the modern city of A Coruña in northwestern Spain lies Castro de Elvina, a fortified Iron Age settlement located in Galicia, less than 10 kilometers from the Atlantic Ocean. Archaeologists first identified the importance of the site in the early 20th century, and systematic excavations beginning in 1947 revealed something unexpected. Beneath layers of soil and vegetation stood the remains of a complex urban community occupied between roughly the 3rd century BCE and the early Roman period. Massive stone walls, carefully organized residential districts, sophisticated drainage systems, monumental architecture, and evidence of long-term planning emerged from the ground. What initially appeared to be a typical hill fort gradually became one of the most intriguing technological puzzles of prehistoric Iberia. The mystery is not whether the inhabitants of Elvina were capable builders. The ruins prove they were. The mystery is how a society operating without modern surveying instruments, steel tools, written engineering manuals, or advanced mathematics produced a settlement whose technical sophistication continues to surprise archaeologists today. The first challenge appears in the settlement's location. Elvina occupies elevated terrain with commanding views of the surrounding landscape. Such positions were common among the Castro culture of northwestern Iberia, Yet Elvina demonstrates an unusually sophisticated adaptation to topography. The builders transformed a naturally uneven hill into a structured urban environment. Houses, streets, defensive works, and public spaces were integrated into slopes that would challenge many pre-industrial construction projects. Modern engineers understand that building on sloping terrain requires continuous management of water runoff, soil stability, and foundation pressure. Failure to account for these factors can lead to structural collapse. Yet portions of Elvina have survived more than 2,000 years despite Galicia's wet Atlantic climate. Annual rainfall in the region frequently exceeds 1,000 millimeters, creating constant erosion pressure. The survival of the settlement suggests a practical understanding of environmental engineering far beyond what is traditionally associated with Iron Age communities. The most visible mystery concerns the fortifications. Massive stone walls surround portions of the settlement, creating multiple defensive layers. These structures were not simply piles of stone stacked for protection. Their placement indicates deliberate exploitation of terrain, visibility, and movement routes. Military historians often compare defensive systems according to how effectively they control access points. At Elvina, attackers approaching uphill would encounter successive obstacles, while defenders retained advantageous sightlines. Similar principles appear in later Roman fortifications and medieval castles. The difference is chronological. Many of the engineering concepts visible at Elvina emerged centuries before medieval military architecture developed comparable solutions. Archaeologists continue debating how the builders planned these defences. Today, such projects would begin with maps, measurements, and geometric calculations. No evidence of formal engineering documents survives from Elvina. Nevertheless, the finished results suggest systematic planning rather than trial-and-error construction. The walls appear where they are most effective, not where construction would have been easiest. Equally fascinating is the settlement's internal organisation. Popular imagination often portrays Iron Age villages as collections of houses that expanded randomly over time. Elvina challenges this assumption. Excavations reveal recurring spatial patterns, organised circulation routes, and districts that appear intentionally structured. Researchers have noted that movement through the settlement was controlled in surprisingly sophisticated ways. Certain routes channel visitors towards specific areas while restricting direct access to others. Such planning resembles principles visible in urban centres throughout the ancient world. At sites like Marzabotto in Etruria or certain sectors of Roman military camps, circulation itself became part of the architecture. Elvina appears to employ similar concepts despite emerging from an entirely different cultural tradition. This raises a difficult question. How did the inhabitants maintain urban consistency across generations without surviving written plans? The archaeological evidence suggests standardization. Standardization is one of the defining characteristics of advanced engineering because it allows builders to reproduce successful designs repeatedly. Yet the intellectual framework behind that standardization remains invisible. The most famous structure at Elvina deepens the mystery further. Known as the Casa de la Exedra, it differs dramatically from ordinary domestic buildings. Its unusual design, monumental appearance, and architectural complexity have generated decades of debate. Some scholars interpret it as the residence of a local elite. Others suggest ceremonial functions. A few researchers have proposed administrative or political roles. None of these explanations fully account for its distinctive architecture. What makes the building remarkable is not merely its size, but its construction quality. The structure demonstrates planning, labour investment, and technical competence, exceeding what would be necessary for ordinary housing. Similar questions arise at other ancient sites where singular buildings stand apart from surrounding architecture. At Machu Picchu, researchers debate specialized functions of certain elite compounds. At Chaco Canyon, monumental structures appear to have served multiple purposes simultaneously. Casa de la Excedra may represent a comparable phenomenon in Atlantic Europe. Another unresolved puzzle concerns stoneworking technology. Granite dominates the geology of Galicia and forms the foundation of much of Elvina's architecture. Granite is durable but notoriously difficult to shape. Even with modern equipment, quarrying and transporting large blocks demands substantial effort. The builders of Elvina possessed neither steel-cutting equipment nor mechanized transport, yet they successfully extracted, moved, and assembled enormous quantities of stone. Archaeological experiments at comparable sites suggest that transporting blocks weighing several hundred kilograms could require dozens of workers using ropes, wooden rollers, sledges, and carefully coordinated labor. The challenge becomes even more impressive when considering elevation changes. Every stone incorporated into walls, houses, and public structures had to be moved uphill. This logistical problem resembles questions raised at hilltop sites throughout the ancient world. Researchers studying Sacsayhuaman in Peru, the hill forts of Britain, and the Oppidar of Celtic Europe repeatedly confront the same issue. The architecture survives. The exact methods remain partially hidden. Water management presents perhaps the strongest evidence for sophisticated practical knowledge. Heavy rainfall creates severe challenges for any hilltop settlement. Without effective drainage, roads deteriorate, foundations weaken, and retaining structures fail. Excavations at Elvina reveal evidence that runoff was carefully controlled. Streets appear positioned to direct water flow. Building placement reflects awareness of drainage patterns. Certain areas show signs of intentional engineering intended to reduce erosion. Modern hydrological models demonstrate that even small alterations in surface gradients can dramatically affect water behavior. Whether the builders understood these effects mathematically is unknown. What is clear is that they understood them practically. Their solutions worked. The Roman period adds another layer of complexity. Elvina did not disappear immediately following Roman expansion into northwestern Iberia. Instead, evidence suggests continuity and adaptation. Indigenous traditions persisted while Roman influence gradually increased. This creates an intriguing technological question. Did local builders adopt Roman techniques? Or did Roman engineers encounter existing knowledge systems worth preserving? Archaeology increasingly suggests that cultural exchange rarely moves in only one direction. Similar patterns appear throughout the Roman world, where indigenous expertise often influenced imperial practices. Perhaps the greatest mystery of Castro de Elvina is not architectural but intellectual. Archaeologists possess walls, houses, drainage systems, roads, and monumental buildings. They can measure dimensions, analyze construction methods, and reconstruct development phases. What they cannot fully reconstruct is the knowledge itself. At nearly 3,000 meters above sea level in Peru's Sacred Valley lies Pisac, an Inca site so precisely engineered that even today, scientists struggle to explain how its builders mastered mountains, water, and stone without modern technology. Spanish chroniclers recorded the ruins centuries ago, but systematic archaeological investigation only revealed their true scale in the 20th century. What initially appeared to be a fortress soon proved to be something far more complex. At first glance, Pisac looks familiar. Stone walls cling to mountain ridges, agricultural terraces cascade down steep slopes, and temples occupy commanding viewpoints overlooking the Sacred Valley below. To most visitors, the site appears to be another impressive Inca settlement. Yet the longer archaeologists study Pisac, the stranger it becomes. Many ancient sites contain mysteries involving a single monument, a particular building, or an unexplained artifact. But Pisac is different. Here the mystery extends across an entire mountain landscape, where every terrace, every channel, every retaining wall, and every carefully positioned structure appears to participate in a larger engineering system that remains only partially understood. The greatest mystery may not be the buildings themselves, but the mountain, because evidence increasingly suggests that the Incas transformed an entire mountainside into a giant engineered machine. The terraces are the most obvious feature, and thousands of visitors photograph them every year, as from a distance they appear to be simple agricultural fields carved into the slopes. However, closer examination reveals extraordinary sophistication. Modern excavations have shown that many terraces contain multiple engineered layers, with large stones forming the foundation, above which lies a drainage layer of gravel and smaller rocks, followed by additional layers of sand and fertile soil that complete the structure. This arrangement resembles principles used in modern civil engineering. The purpose was not merely to grow crops, as the terraces controlled water, stabilized slopes, prevented erosion, distributed moisture, and protected the mountain itself. Researchers studying Inca agricultural systems have estimated that some terrace complexes dramatically reduce surface runoff compared with natural slopes, allowing water during seasonal rains to penetrate downward through carefully designed layers rather than rapidly washing soil away. Remarkably, many of these systems continue functioning after roughly 5 centuries, whereas modern retaining walls frequently require maintenance after only decades. Pisac's terraces continue operating after hundreds of years of earthquakes, storms, and environmental change. How such durability was achieved remains unclear, as no surviving Inca manuals explain the calculations, no architectural blueprints have been found, and no written engineering instructions survive, yet the results remain visible across the mountain. The question becomes even more intriguing when considering the terrain itself, as Pisac occupies one of the most challenging environments imaginable for large-scale construction. Steep slopes dominate the landscape, altitude complicates labor, heavy seasonal rains threaten stability, and gravity constantly attempts to pull entire sections of mountain downhill. Modern engineers facing such conditions rely on geological surveys, soil testing, computer modeling, and advanced measurement equipment, yet the Incas possessed none of these technologies, at least none that archaeology has identified. Nevertheless, the terraces follow the contours of the mountain with astonishing consistency, and their geometry appears deliberate rather than improvised. Many align perfectly with natural formations, while simultaneously maintaining structural stability, suggesting a sophisticated understanding of geology, though the source of that knowledge remains uncertain. Water may represent the site's most impressive technological achievement, as across the ancient world, water management often determined whether civilization flourished or collapsed. The Romans built aqueducts, the Nabateans engineered Petra's hydraulic systems, and ancient Persians developed qanat networks extending for kilometers underground, yet the Incas followed a different path. Rather than forcing nature into rigid channels, they often designed systems that worked with the landscape itself, and Pisac demonstrates this philosophy on a massive scale. Archaeologists have identified channels, drainage features, and water control mechanisms distributed throughout the site, some of which remain only partially explored while others are hidden beneath later deposits. The visible elements alone suggest a complex network designed to regulate rainfall and protect infrastructure. But what remains unknown is how much of the original system still lies concealed underground. Many researchers suspect that substantial portions have yet to be discovered, and if true, then the engineering complexity visible today may represent only a fraction of the original design. The stonework introduces another layer of mystery, as like other major Inca centers, Pisac contains examples of exceptionally precise masonry. Some stones fit together so tightly that inserting even a thin blade between them is difficult, an observation often repeated but frequently underestimated in significance. Creating such joints requires more than patience, as it demands measurement, planning, and quality control. Each stone possesses a unique shape, many containing multiple angles and irregular surfaces, and a mistake on one contact point could affect every adjoining block, yet the finished assemblies often appear seamless. Comparisons with other ancient civilizations highlight the achievement. As Egyptian builders mastered monumental scale, Roman engineers excelled at arches and concrete, while the Incas specialized in precision fitting under seismic conditions. In earthquake-prone regions, rigid construction often fails, but Inca masonry appears to absorb movement while maintaining stability, leading some scholars to argue that this characteristic helped many structures survive earthquakes that destroyed later colonial buildings. However, the underlying methods remain debated, and exactly how the builders measured, tested, adjusted, and finalized these stone interfaces is still uncertain. The location of Pisac raises additional questions, as many structures occupy seemingly strategic positions overlooking valleys and mountain horizons. Some alignments may relate to astronomy, while others may connect to sacred geography, reflecting the Inca view of mountains, rivers, and celestial bodies as interconnected elements within a larger cosmological framework. Several researchers have proposed that certain architectural orientations correspond to solar events, seasonal cycles, or significant landscape features, and if these interpretations are correct, then Pisac functioned as more than an agricultural center. It may have served simultaneously as an observatory, ceremonial complex, administrative hub, and environmental monitoring system, a multifunctional design that would require extraordinary planning. Engineers would need not only to understand construction and hydrology, but also possess knowledge of astronomy, geography, and seasonal agriculture, making the integration of these disciplines one of the site's most fascinating aspects. Logistics create yet another unsolved puzzle, as every stone visible at Pisac had to be extracted, transported, positioned, and fitted into place, all at high altitude on steep terrain. The Incas possessed no wheeled transport system for large construction projects, lacked draft animals capable of moving massive loads comparable to oxen, and had no steel machinery, combustion engines, or hydraulic cranes. Yet monumental architecture emerged across the Andes, and Pisac joined sites such as Machu Picchu, Ollantaytambo, and Sacsayhuaman in presenting the same fundamental question. How did ancient builders repeatedly achieve results that appear disproportionate to their available tools? The answer remains incomplete, as archaeologists have proposed combinations of ramps, human labor, rope systems, and ingenious planning, which account for part of the process, though whether they explain everything remains open to debate. Incallajta lies high in the eastern Andes of Bolivia at an elevation of nearly 2,950 meters above sea level. Hidden between steep mountain ridges and dry valleys, the site was first documented by Spanish chroniclers in the 16th century, but serious archaeological investigation did not begin until the early 20th century. Today, researchers consider Incallajta one of the largest and most mysterious Inca sites ever discovered outside modern Peru. The city covers more than 80 hectares and contains massive stone walls, ceremonial plazas, agricultural terraces, storage facilities, and military structures. What makes Incallajta unusual is its location. Unlike Machu Picchu, which was hidden deep within isolated mountains, Incallajta stood directly on the dangerous frontier between the Inca Empire and the eastern lowland tribes, especially the fierce Chiriguano warriors. This was not simply a ceremonial city. It was a strategic fortress placed at the edge of an empire that controlled almost 4,000 kilometers of South America. But the deeper archaeologists studied Incallajta, the stranger the site became. One of the greatest mysteries surrounding Incallajta is how the Inca managed to construct such a massive complex on unstable mountainous terrain without iron tools, wheeled transport, or modern engineering equipment. Many of the surviving walls still stand after more than 500 years of earthquakes, seasonal flooding, and temperature fluctuations. Some stone blocks were shaped so precisely that even modern measuring tools reveal gaps of only a few millimeters between surfaces. Similar techniques are found at Sacsayhuaman in Peru, where stones weighing more than 100 tons fit together with astonishing precision. However, Incallajta presents an additional challenge. The entire complex was built on sloped terrain vulnerable to erosion and seismic activity. Modern engineers studying Inca masonry discovered that many walls were intentionally tilted slightly inward. This subtle angle distributed seismic energy throughout the structure during earthquakes. In laboratory simulations, researchers found that polygonal Inca stonework absorbed vibration significantly better than rigid European masonry from the same historical period. Yet the biggest question remains unanswered. How were these stones transported across steep mountain terrain? Some quarries linked to Incallajta are located kilometers away from the main complex. Moving multi-ton blocks uphill without wheels or draft animals capable of carrying heavy loads would have required extraordinary coordination and manpower. Experimental archaeologists attempting to recreate similar transportation methods discovered that even moving stones weighing 2 to 3 tons over rough slopes required dozens of workers using ropes, ramps, and wooden rollers. Incallajta contained stones far larger than that. The most mysterious structure at Incallajta is the gigantic Calanca, a rectangular hall measuring approximately 78 meters long and more than 25 meters wide. It is believed to be one of the largest roofed buildings ever constructed by the Inca civilization. This immediately creates a major engineering mystery. The stone foundations and column bases indicate the building once supported a massive roof structure, but constructing a roof of that scale at high altitude would have been extraordinarily difficult. Strong Andean winds, seasonal storms, and dramatic temperature changes would place enormous stress on wooden support beams. Archaeologists estimate that the roof may have required hundreds of massive timber beams. The problem is that large trees do not naturally grow at that elevation. The wood likely came from distant subtropical forests east of the Andes, possibly transported from regions dozens of kilometers away. Even today, transporting heavy timber through those mountain routes without roads would be extremely difficult. Some researchers estimate that the labor force required for the Calanca alone may have numbered in the thousands. What confuses experts even more is the purpose of such a colossal hall. The structure was far larger than most known military barracks. Some believe it functioned as a ceremonial gathering center, capable of hosting political assemblies, rituals, or elite administrative meetings. Others argue it may have been designed to demonstrate imperial power near the empire's frontier. But no definitive answer exists. Like many major Inca sites, Incallajta appears to contain sophisticated astronomical alignments. Several doorways and walls line up with the position of the sun during solstices and equinoxes. Researchers studying the site noticed that sunlight passes through specific openings at precise seasonal moments, illuminating ceremonial sectors of the complex. This suggests Incallajta may have functioned partly as an astronomical observatory. The challenge is understanding how the Inca achieved this level of accuracy. The mountainous terrain surrounding the city creates distorted horizons that complicate solar observations, yet the alignments remain remarkably precise. At Machu Picchu, similar solar alignments have an error margin of less than 1 degree. Some researchers believe Incallajta may have achieved comparable precision using only naked eye astronomy and horizon markers. This required advanced long-term observation of celestial cycles. The Inca possessed no written mathematical system comparable to Greek astronomy, yet they successfully integrated solar tracking into architecture across thousands of kilometers of mountainous terrain. Even more mysterious is the possibility that Incallajta's ceremonial layout mirrored cosmological beliefs tied to the Milky Way, which the Inca considered a sacred celestial river. Some archaeologists argue the city's orientation reflects symbolic connections between the heavens and imperial authority. Perhaps the most underrated mystery of Incallajta is its water management system. The region experiences extreme seasonal variation. During rainy periods, water descends violently from surrounding mountains. During dry seasons, water becomes scarce. Yet the Inca engineered a network of canals, terraces, drainage channels, and reservoirs capable of stabilizing agricultural production. Some channels still function today after centuries of abandonment. Modern hydraulic engineers studying Inca systems discovered that many channels maintained incredibly precise gradients. If the slope was too steep, water would erode the stone lining. If too shallow, the flow would stagnate. In several sections of Incallajta, the gradient varies by only tiny fractions across long distances. This precision becomes even more astonishing considering the lack of modern surveying instruments. The agricultural terraces surrounding the city also reveal sophisticated environmental adaptation. By creating stepped farming platforms, the Inca reduced erosion while maximizing water retention. Similar systems across the Andes remain agriculturally productive after hundreds of years. NASA researchers studying ancient agricultural resilience have even compared Andean terrace systems to sustainable farming solutions for harsh environments today. At first glance, Incallajta appears to be a military fortress built to defend the eastern border of the Inca Empire. Massive defensive walls and strategic positioning support that theory. However, the city contains an unusually high concentration of ceremonial architecture. Large plazas, ritual spaces, sacred alignments, and elite compounds suggest Incallajta served functions far beyond warfare. Some historians believe the site acted as both a military command center and a symbolic demonstration of imperial control over frontier populations. This dual purpose may explain its immense scale. Unlike isolated fortresses designed purely for defense, Incallajta projected political and spiritual authority. It represented the physical edge of one of the largest empires in pre-Columbian America, an empire controlling nearly 12 million people at its peak. The city may have been intended to intimidate neighboring tribes not only with military strength, but with architecture itself. One of the strangest aspects of Incallajta is evidence suggesting parts of the city were never fully completed. Some structures appear unfinished. Certain walls abruptly stop. Construction zones show signs of sudden interruption. Archaeologists believe major building activity may have ceased rapidly during the early 16th century. Then the city was abandoned. The arrival of the Spanish dramatically destabilized the Inca Empire after the capture of Emperor Atahualpa in 1532. Civil war, disease, and political collapse spread across the Andes within only a few decades. But some researchers suspect Incallajta's abandonment may have started even earlier due to pressure from Chiriguano invasions. Historical accounts describe repeated attacks on Inca frontier settlements in this region. If true, Incallajta may represent a massive imperial project interrupted before completion, a frontier mega-city abandoned during the collapse of an empire. Far inside Egypt's western desert near the Kharga oasis, more than 200 kilometers from the Nile Valley, lies Ein Labaka, a forgotten Roman-era settlement surrounded by endless Sahara. Modern archaeological surveys in the 20th century initially identified the site as a small frontier outpost, but excavation quickly revealed something far stranger. Beneath the collapsed mud brick walls were traces of advanced water systems, industrial activity, thermal engineering, and long-term habitation in one of the harshest environments on Earth. Average summer temperatures in the region regularly exceed 45 degrees Celsius, while sandstorms and extreme day-to-night temperature fluctuations continuously erode exposed structures, yet the settlement survived for centuries. That alone became the first mystery. At first glance, Ein Labaka appears insignificant compared to famous Egyptian monuments. There are no pyramids, giant statues, or royal tombs. But archaeologists became increasingly puzzled by one simple question: how did a permanent settlement survive here at all? The surrounding desert receives almost no rainfall. Surface water is nearly non-existent. Modern satellite studies of the region show that sustaining agriculture in this part of the Sahara without engineered groundwater extraction would be almost impossible. Yet evidence from pottery remains, grain storage areas, and agricultural traces suggests the settlement supported a stable population for long periods. This immediately separated Ein Labaka from ordinary desert forts. Roman frontier stations across North Africa typically relied on nearby rivers, caravans, or regular military supply chains. Ein Labaka, however, functioned in near isolation. Some researchers now compare it to a self-contained survival machine rather than a conventional settlement. The greatest mystery surrounding Ein Labaka is its hydraulic system. Excavations uncovered deep wells, underground channels, reservoirs, and carefully engineered water distribution structures buried beneath the desert surface. Some wells penetrate extremely hard geological layers at depths reaching dozens of meters. Even with modern drilling equipment, constructing and maintaining such systems in Sahara conditions is difficult. Ancient Roman iron tools were relatively primitive by modern standards, yet the excavation marks suggest astonishing precision and planning. Researchers believe parts of the system may have been inspired by Persian Qanat technology, an ancient underground water transport method capable of carrying groundwater across long distances while minimizing evaporation. But Ein Labaka exists far from the major Persian engineering centers traditionally associated with Qanats. This raises an unresolved question. Did Roman engineers independently adapt similar hydraulic principles for the Sahara, or was there a much larger transfer of technical knowledge across ancient trade networks than historians currently understand? Hydrological simulations conducted on desert settlements in Egypt suggest that maintaining a stable water supply for even a few hundred people would require precise calculations of groundwater recharge rates and seasonal extraction limits. Over-extraction would have collapsed the system within years, yet Ein Labaka appears to have remained active for generations. That level of environmental management feels remarkably modern. Another major mystery lies in the construction materials themselves. Ein Labaka was built primarily from mud brick, one of the oldest and usually most fragile building materials in human history. Under ordinary conditions, mud brick rapidly deteriorates under wind erosion and thermal stress. Yet many sections of Ein Labaka remain standing after nearly 2,000 years of exposure to Sahara conditions. Material analysis revealed that the bricks were not made from ordinary mud alone. Microscopic studies identified unusual mixtures of mineral salts, clay compositions, and organic fibers embedded within the structure. Some bricks display unusually dense internal bonding compared to typical Roman-era desert construction. Modern experiments attempting to replicate the material found that certain mineral combinations significantly improved resistance to heat cracking and wind erosion. However, the exact formula has not been fully reproduced. This is especially strange considering the logistical challenges. Ein Labaka existed in an isolated desert zone with limited natural resources. Transporting specialized minerals across the Sahara would have been expensive and dangerous. Yet the builders somehow produced construction materials capable of surviving one of the harshest climates on Earth. Some archaeologists compare the mystery to Roman concrete technology found in Mediterranean harbors. Ancient Roman marine concrete still resists seawater after 2,000 years, partly because of volcanic chemical reactions modern engineers only recently began to fully understand. Ein Labaka may represent a similar lost branch of environmental engineering adapted specifically for desert survival. Perhaps the most controversial mystery at Ein Labaka involves evidence of industrial activity hidden within the ruins. Archaeologists discovered traces of furnaces, ash deposits, storage chambers, mineral processing zones, and unusually high concentrations of burned material embedded in certain areas of the settlement. These discoveries suggest Ein Labaka was not simply a military outpost or caravan stop. Something was being produced here, but no one knows exactly what. One theory proposes the site functioned as a specialized production center for heat-resistant construction materials. Another suggests mineral extraction or processing connected to Roman trade networks moving through the Sahara. Chemical analysis of residue found near furnace structures revealed elevated concentrations of iron compounds and silica, though not enough evidence exists to confirm large-scale metallurgy. What makes the mystery even more intriguing is the location itself. Industrial production requires fuel, water, labor, and stable logistics. The Sahara provides almost none of these naturally. Running furnaces in extreme desert conditions would have consumed enormous resources. Yet the evidence clearly points toward organized industrial activity. Some researchers believe Ein Labaka may have served as a strategic manufacturing station, supporting long-distance desert caravans traveling between Roman Egypt and sub-Saharan trade routes. Others argue the industrial traces could indicate experimentation with local mineral resources that have not yet been fully identified. There is also the possibility that much of the original settlement remains buried beneath sand layers still untouched by excavation. Ground-penetrating radar surveys in nearby desert regions have repeatedly revealed hidden structures invisible from the surface. If larger industrial sectors remain undiscovered beneath Ein Labaka, the true scale of the settlement may be far greater than currently believed. This transforms Ein Labaka from a forgotten desert ruin into something far more unsettling, a technological outpost operating deep inside an environment where sustaining even basic life should have been extraordinarily difficult. The architecture of Ein Labaka reveals another layer of sophistication. Building orientation, corridor placement, wall thickness, and airflow pathways appear intentionally designed to regulate internal temperatures. Some narrow passageways functioned similarly to pressure ventilation channels. Air entering shaded sections accelerated through confined spaces, naturally reducing interior heat. Computer thermal simulations performed on comparable desert structures show that passive cooling systems like these can reduce internal temperatures by 8 to 12 degrees Celsius. That difference can determine survival in extreme desert environments. Modern sustainable architecture increasingly uses similar passive cooling principles to reduce dependence on artificial air conditioning. Yet Ein Labaka implemented these concepts nearly 2 millennia ago. The mystery is not simply that ancient people understood cooling. Many civilizations adapted to climate. The mystery is the precision. The system appears engineered systematically across the settlement rather than developing randomly over time. Some historians argue Roman frontier engineers may have possessed a much deeper understanding of airflow dynamics and thermal behavior than surviving historical records suggest. What do you think Ein Labaka truly was? Just a forgotten desert outpost, or evidence of ancient engineering knowledge far ahead of its time? Share your thoughts in the comments below. Rising above the Rhodope Mountains of southern Bulgaria near the modern town of Asenovgrad is a massive stone plateau more than 1,200 meters above sea level. From the air, it looks almost unnatural. A giant slab of exposed granite carved with channels, pits, basins, geometric cuts, and strange depressions that seem too deliberate to be random geology. The site is known as Belintash Plateau, and for decades it has remained one of the least understood ancient sites in Eastern Europe. Unlike famous megalithic locations such as Stonehenge or Machu Picchu, Belintash receives little international attention. Yet many archaeologists and geologists agree that some of its features are extremely difficult to explain using conventional Bronze Age technology. The discovery of Belintash as a serious archaeological site began relatively late. Although local legends about the plateau existed for centuries, systematic studies only intensified during the 20th century when Bulgarian archaeologists noticed unusual patterns carved directly into the granite surface. Excavations revealed ceramic fragments, ritual remains, and evidence connected to the ancient Thracians, a civilization that occupied large parts of the Balkans more than 3,000 years ago. But the deeper researchers looked, the stranger the plateau became. The first major mystery is the stone processing itself. Belintash is composed primarily of granite, one of the hardest natural construction materials commonly encountered by ancient civilizations. Granite measures around 6 to 7 on the Mohs hardness scale, meaning it is harder than bronze and difficult even for iron tools to shape efficiently. Yet across the plateau are dozens of straight channels, flattened surfaces, drilled depressions, and sharply defined cuts extending across large sections of exposed rock. Some grooves maintain surprisingly consistent depth over long distances, while others intersect at angles that appear intentionally geometric rather than natural. This becomes difficult to explain when compared to known Bronze Age stoneworking methods. Ancient Egyptians, for example, processed granite extensively at Aswan and inside pyramids, but they left clear chisel marks, pounding traces, and visible tool damage. Even with enormous labour forces, shaping granite was incredibly slow. Experimental archaeology suggests that smoothing 1 square metre of granite using primitive hammerstones can require dozens of labour hours. At Belintash, however, flattened areas extend across tens of square metres. If all of this work was done manually, the labour investment would have been enormous for a mountain sanctuary occupied by a relatively small population. Some researchers argue that many of the formations could be natural erosion, but this explanation struggles to account for the repeated linear patterns and the organisation of several channels. During heavy rain, water flows through the carved grooves in highly controlled ways, almost like a primitive hydraulic system. Certain basins fill sequentially, while others drain through narrow cut paths. This has led to theories that Belintash may have functioned not only as a ritual centre, but also as a type of ceremonial water management system. That possibility is significant because advanced hydraulic engineering is usually associated with civilizations such as the Romans, Nabateans, or Maya. At sites like Petra, engineers created highly efficient water channels capable of sustaining entire desert cities. Belintash is far older and far smaller, yet some of its water flow features appear surprisingly intentional. Researchers have proposed that rainwater moving through the channels may have held ceremonial or astronomical importance, possibly linked to seasonal observations. Another unexplained feature is the series of small circular and oval depressions scattered across the plateau. Some are isolated, while others appear grouped into patterns. Local theories often describe them as star maps, suggesting they may represent constellations such as Orion or the Pleiades. While many archaeologists remain skeptical of astronomical interpretations, the geometric arrangement of certain groups continues to raise questions. Some depressions appear too regular to be random weathering, and several show signs of repeated shaping or smoothing. The problem is technological. Creating uniform depressions in granite normally requires either persistent abrasion or rotational drilling methods. Yet there is little evidence that the Thracians possessed advanced drilling technology, comparable to later Roman or Hellenistic systems. Similar debates exist at other ancient sites around the world. In Peru, polygonal stonework at Vilcashuaman displays precision that continues to challenge modern assumptions about pre-industrial engineering. At Belintash, the mystery is smaller in scale but equally frustrating because the technical evidence appears more advanced than the surrounding archaeological culture would normally suggest. One of the most controversial mysteries involves the possibility that Belintash functioned as an astronomical observatory. Several carved lines and depressions align roughly with solar positions during equinoxes and solstices. Researchers have noted that sunlight interacts with parts of the plateau differently during specific seasons, potentially creating shadow markers or illumination points. Similar systems existed in ancient cultures worldwide. At Chichen Itza, the famous pyramid of Kukulkan creates a serpent-shaped shadow during equinoxes. At Nabta Playa, stone arrangements may have tracked seasonal celestial movements more than 6,000 years ago. But Belintash presents a problem. There is no massive architectural structure, no tower, and no obvious observatory platform. Instead, the plateau itself appears to have been modified directly into an observational surface. If intentional, it would represent a highly unusual form of prehistoric astronomical engineering integrated directly into natural geology. Geologists have also identified minor magnetic anomalies in the surrounding region. These anomalies are not extreme enough to support pseudoscientific claims about energy portals, but they are scientifically interesting because ancient cultures repeatedly selected geologically unusual sites for ritual construction. Göbekli Tepe, Delphi, and several Andean ceremonial centers were all positioned near distinctive geological formations or fault zones. Some scientists believe ancient societies may have been unusually sensitive to environmental features such as underground water movement, magnetic variation, or acoustic resonance. Acoustics may be another overlooked mystery at Belintash. Certain parts of the plateau produce unusual sound reflections due to the flat granite surfaces and surrounding cliffs. Even small voices can echo unexpectedly in particular locations. This has led some archaeologists to speculate that rituals performed there may have intentionally incorporated acoustic effects, similar to ceremonial structures found in Malta's ancient Hypogeum, where specific frequencies resonate with unusual intensity. The survival of the carvings themselves is another unresolved question. Belintash experiences harsh mountain weather, including freezing winters, strong wind exposure, and constant water erosion. Granite slowly fractures through freeze-thaw cycles, where water enters microscopic cracks, freezes, expands, and gradually breaks apart the rock. Over thousands of years, shallow carvings should become heavily degraded, yet many channels and depressions remain surprisingly visible today. This suggests two possibilities. Either the carvings were originally much deeper and more precise than they appear now, or parts of the plateau were maintained over very long periods by repeated human activity. Both explanations imply a level of long-term occupation and technical effort that archaeologists still struggle to fully reconstruct. Perhaps the most unsettling aspect of Belintash is not what researchers know, but what they cannot explain. The plateau contains enough evidence to confirm deliberate human modification, but not enough evidence to clearly reveal its true purpose. It may have been a Thracian sanctuary, an astronomical calendar, a ritual water system, or something combining all three. Every explanation solves one mystery while creating another. What do you think Belintash really was? An ancient observatory, a sacred ritual site, or evidence of a lost engineering knowledge far ahead of its time? Share your thoughts in the comments below.